Hello, everyone. This is Drew Crawley again, and I'm going to start where we left off yesterday. After we get through weather data, I want to take a break and go back to try to answer some of the questions we didn't get yesterday, and uh, we'll get the the questions that have come up as well since then. So let's start. We were going to cover weather data. Weather data, it's one thing to talk about whether the weather and climate are not the same thing. And so we need to understand what we're doing and how we're using data to be able to understand that. This chart is an example of what's happening for a 12-hour period at one of the national labs in Colorado. And you see the green is the solar radiation, brown is direct, and you see some drop-offs in that in the afternoon. And that's primarily because in afternoon and summer on the Front Range in Colorado, it does tend to cloud up. It may or may not rain, but we have temperatures changing throughout the day, wind as well. And you see that's changing quite rapidly. These are, I think, 1 minute data for this. And most of the weather data that we get or that is summarized for us is in 1 hour chunks. So the vertical lines. So you may miss some of those things that are going on there. The other thing is to understand the difference between weather and climate. Weather is what's happening now. It's what the app on your phone says. It's what they talk about on TV or radio. It's a snapshot of what's going on. Climate, on the other hand, is a long-term view of it. Now, how long that view is makes a difference, but it's the generally prevailing weather conditions of a whole bunch of different variables for that. And you may hear somebody say, oh, it's 5 degrees above normal, or that's 5 degrees colder than normal. Well, normal is a meteorological thing that the data scientists do. They take a snapshot of 30 years and look at that. So when they talk about normal right now, we're talking about the past 30 years up through 2020 for that particular case. And so you're going to see that has an average of that for a particular case. In simulation, we need multiple ways of looking at climatic data or even weather data. We use design conditions for peak heating and cooling, and we have a great resource I'll show you a little later from the ASHRAE fundamentals, talking about temperature, humidity, solar, wind, and other variables as well. But when we're doing our simulations, we need more. We need to have some representation of what's going on in that climate. We have typical hourly weather data. We have actual hourly weather data. Say you want to calibrate to a utility bill. And there are many sources now for creating your own future hourly data for that. So we'll talk a little bit more about them. So first, let's talk about a design condition. Generally, we're looking at something that has dry bulb, wet bulb, dew point temperatures, and wind speed at various frequencies of occurrences. In the ASHRAE handbook, which is the best source globally for this, and it's often cited by many other countries in what they use, but it's a statistical summary from the past 20 to 30 years. 20 because some stations don't have a lot of data till recently, but that's kind of the break. So for the 2021 handbook, that includes data up through 2019. So if you've been following what's been going on in climate change, that doesn't include the last 3 years, including the last year and actually up through this year are the hottest on record. In fact, we're already looking at 11 straight months with temperatures hottest on record globally. So what happens in the design conditions, they are percentiles of data, and a percentile is nothing more than a number of hours that the design condition can be expected to be exceeded. based on how many of our years of data. So if we're looking at 1%, that's 88 hours a year that you might expect the temperature to be above that. Why don't we design to the worst condition? Because you're going to pay a lot to be able to do that. And most of the time, there's enough mass in the building and other things to sort of float through those, and small variations are not going to work. So for heating, it's recommended to use 99%, and 99% again is like 1, but that means 99% of the time it's going to be warmer than that. Again, it's about 88 hours a year. Also, annual 1% has been recommended in the past. At this point, though, ASHRAE is recommending using monthly cooling percentiles, with 5% being the recommended. And they're using 5% because it's about equivalent to the 1% annual cooling. So if you look at the chart there, there's the two red areas. There's the heating dry bulb conditions for that particular location, and the large area is the monthly design conditions for the 5%. The data source for this is the U.S. National Centers for Environmental Information. They're part of NOAA, and they collect data globally, so it's not just U.S. data. It has stations around the world. So there is an app to be able to do this, the ASHRAE Station Finder Weather Data Viewer. Each of the circles represents the number of stations that are nearby. It's all station-based, but you can zoom in. Here we're zooming into New York and being able to start looking at some of the various locations, and you can click on one of those and it'll tell you where it is, etc. So typical meteorological sets have been primarily used for doing most energy simulation. And simulation tools really shine when it comes to comparison of alternatives. So if you're looking to compare something, this is a typical condition, and also compliance with codes and rating systems as well. But there have been no explicit efforts to represent the extreme conditions, and you may not see some of the things like we had last year where we had extreme conditions. Temperatures, I mean, globally, we're seeing temperatures in India right now that are over 50 C, over 122 degrees. And the Middle East has seen temperatures much higher than that as well. Those you probably won't see in most of these files. They're not intended to represent the design conditions, but sometimes I think as we get better data, they are representing that better. In the US, we have in the chart you see there TMY data, and so for many years, up even until the late 2000s, we didn't have a lot of data for the US, just 200 and some locations. The last data set you see there, TMY3, from one of the labs, the data is almost 20 years out of date at this point. There's a newer data set, TMYX, which has 16,000 locations globally, and I think it has over 2,000 in the US. More data as it comes online. The other thing, sometimes we need actual weather data. We need 2022 or 2021 or something like that. When we're trying to calibrate a model to utility bill, that means we have more accurate representation of what's going on outside. And so that it'll allow you to look at that better than the typical, the TMY will do. There are lots of different sources for there. I mentioned NCEI, you can get that data, but there are other for fee groups that will also provide you data for a particular location and a particular year. But the issue for all of this is how complete are they? NCEI, for example, includes temperature, humidity, wind, but no solar radiation. So you either have to calculate or you have to find another source. A lot of the ground stations don't bother calculating that because the vast majority of ground stations are located at airports, and solar radiation is not what they need for aviation, and that's really the key thing there. The good news is there are other tools out there, other data sets that now have solar radiation data available on a broad range of locations, often a gridded product. so those can help supplement what's in some of the other data sets. So this might be a situation where we've got missing data and you've has some interpolation that has to be done. You see, it makes the data a little odd. The good news is recent data is actually pretty complete. It's older data sets. You get back in the 60s, 70s, and before, and you're going to find missing periods, and so that there is an issue there. So does it matter? Well, this is Washington National Airport. I live in Washington, D.C. This is about 6 miles from my house. And so this is a medium office building, about 54,000 square feet, one of the DOE prototypes or reference buildings. And I've simulated it for all the available data up through 2021. I haven't updated it yet for the last 2 years. It starts in 1937, which is pretty remarkable. This is the only data set that has data going back 80 some years complete. There are many locations in Europe, but they have big gaps in the 40s and 50s post World War II. So you see some random variation there. This is actually a packaged unit, but I think it's a constant speed fan, so we're not getting a lot of variation there. But if I drew a line through the TMY, which are the two on the right, that shows that it's doing what it's supposed to. It's about in the mid range. You'll see some outliers. 2010, for example, had both a very cold winter and a very hot summer, so that brought both the energy up. But you see the variation going on there. Actually, TMY is doing a pretty good job. If we take out some of the scheduled things like lights and other things and just look at the proportion, the heating, cooling, and fans, you see a lot more variation there, more on the range of 20% or more. But again, the TMY does what you expect it to do. So future weather, there are a number of different ways of doing that. There are the models that come out of the IPCC that predict future conditions on an hourly basis for a gridded product. And so some of the methods, statistical downscaling of that allows you to try to get something that's more localized to what you're doing. Statistical models will give you reasonable results. Both of those are actually very computationally intensive for that. The most common one is time series morphing or adjusting, and I'll show you an example of that in just a minute. One of the ones that give you an easy way to look at it is an analog. What is my future climate going to look like, and which city now has that? So I could actually go and look at some of that. So this might be a condition where Houston is going to look like Ciudad Monte, Mexico. So it's 4 degrees warmer and 27% wetter than summer in Houston, which Houston's already pretty hot, humid there. So that is an idea of an analog, and you'll see maps like this for a number of different cases. So this is an example of morphing. This is from Los Angeles TMY2 file. The yellow is the existing dry bulb, and then there are 4 lines. 2 of them are basically on top of each other, but representing the GCM, the global climate models output, and how the 4 scenarios that they're using. And so there's a base diurnal temperature, high to low for the day, temperature spread. There's also a scenario diurnal temperature, and that is often a little bit less. It's sort of compressed. The nighttime temperatures remain higher. And so you'll see some of that. And then there's also the scenario delta temperature. So there are lots of things going on in morphing. It's not just simply taking the scenario delta temperature, but it's also changing the diurnal temperature as well to adjust for that. So there are a number of models out there that do a good job of this. There are also tools that derive the data directly from the GCM and make that easy to look up. There are TMY data sets for a number of different things. This is a small subset of it. I can assure you that's a lot of data out there available, and you see various things here. So depending on where you are, there are data for that. And so look for local sources where possible. There are, because of course they're going to pay attention to local idiosyncrasies of the climate. Future weather, there's some tools out there. The first one is the CC World Weather Gen. That's not been updated for a while, and it uses a very older version of the data set. And you see some of the there. So some of the two, I think the EPW Shift R and the Future Weather Generator, both relatively new, and they're open source and available. So they give you recent data, the AR6 being the most recent. Weather Shift commercial products, you can buy individual files for a fee for that. There are other data sets. For example, there's a morph data set from Germany, one from CIBSE, two downscaled ones, Canadian Future Weather, and which has got 564 locations for Canada, and Future Weather data for North America, which is a project underway by one of the national laboratories. So let me take a look at questions so I can.
Yeah, there's a few questions here. And I can try to respond to some of these just in the chat so that we don't worry about the TMY difference.
Okay, let's see, I'm trying to. Jose, yeah, I think we have a link to the UCLA psychometric chart. If not, I'll make sure it's in the chat before the end. Okay. What's the difference? I'll start at the bottom. Asia's asked what the difference between morphed and downscaled. Morphed takes an existing file and changes it to match what the future says it's going to be. Downscale takes the GCM models, which are often on a 1 degree by 1 degree latitude longitude, and brings them down to local scale. So there's some interpolation to get between multiple points to yours. I think the downscaled is more accurate, but we're talking about a lot of computational. Jose asks, what's the difference between TMY versus TMY2? Primarily years that were used, there's slight differences in the data sets, but frankly, using more recent data, I think is pretty important. Using data that's 20 years old, not reflecting the changes that we've already seen is sort of a difference. Let's see. Sean says there's some risk with analogs. Higher latitudes will also have more variability and continue at extremes that should be included with model. Sean, I perfectly agree. I think the analog is just to give you an idea of how the future weather may have been. So that's the that's an important point to understand that, for example, if your location's in Houston, but the place the analog says it's inland, it'd probably be very different because one will be coastal and one won't. So you have to, you take it with a grain of salt. Okay. Richard asked for the difference between mean coincident wet bulb and 99 or 99.6 design wet bulb. That's a great question. What happens, there are often, if you're looking at percentile, you'll have like a 99% heating dry bulb, and then there'll be a mean coincident wet bulb associated. For that temperature, go back through the data and find the average, the mean wet bulb that correlates to that. And similarly, there is a percentile for wet bulbs. So if wet bulb's important for what you're doing design, and sometimes for various portions of that, wet bulb may be more important, like cooling tower design. So you would have a wet bulb percentile and a mean coincident dry bulb to go along with that. Let's see. George asks, which of all possible TMY should we use according to 90.1? 90.1 just says hourly data. It doesn't specify which, but I recommend using the more recent data, partly because what we're seeing is a real shift, and I didn't show it wasn't quite as apparent, but on the chart I showed you for Washington D.C., there's a big shift, a drop of 10 to 15% in heating energy going on for a lot of locations, and cooling is coming up some, but we're seeing a big shift downward, and that may affect your things. Let's see. Luis asked, is there a way to include the heat island effect? There are some models that will produce heat island. They're often they're very specific urban design models. And yes, so there is work there. And NOAA here in the US has been trying to calculate that. I know they came through Washington, D.C. in 2018 on an August day and recorded temperatures all around the city. And the difference between the cooler temperatures, we actually have a national park that runs through the city, in that versus the commercial core was on the order of 15 degrees difference in temperature. And so there is quite a bit of difference in temperature. And for National Airport, it is on the lower side of that because it's actually surrounded on three sides by a river. So, but yeah, if you do a little bit of searching on heat island calculations, there are methods out there. Let's see. Annual percentiles. Jose asking again. Its percentile is just a number of hours. So if you take 8760 hours and say 1%, 1% of 8760 is about 88 hours. And so that's what it means on an annual basis. And Jose also asked, for places that have a lot of stations, what would be a good rule of thumb to use a radius applicable to the station? I would look at elevation change. I'd look at proximity to water to make sure that they're similar. So if you have a location on the coast, you want to try to find, if you're building or projects on the coast, you want to find a location that is similar to that. You don't want to take something that's away from the water, because the water will definitely affect that. So, I mean, some cases it's very difficult. There are large areas of Africa, for example, that have very few stations, at least station data, although there are gridded data products from satellite now for that. Let's see. Okay. Sam, do you want to talk about the last question about central plant? Or actually, you do cover that later, don't you?
Yeah, we'll talk about that later.
Okay. And Keith's asking, considering all the permutations design, imagine keeping track of the versions of models takes a big effort. Yeah, that is where it comes down to. It is definitely documenting each simulation you're doing, so that when you go back later, a month or whatever, however later it is, you can figure out what you did. It's often difficult from trying to comb through a file, and better if you have documentation on that. There's not anything really in 209. I've seen various attempts at just creating a spreadsheet that talks about that. Some of the spreadsheets that are available with the DOE representative buildings that P&L does actually have a good set of spreadsheets with those to show what all the variables are. So that might be a starting point, because there are literally thousands of inputs. So, Sam, do you want to talk about the questions from yesterday about resources for old buildings?
Yeah, and I think we'll talk about some of that as we get towards the end of today. So there were some questions as we were talking about data collection Let me pull up those questions from yesterday. Yeah, so questions about data for older buildings, existing buildings, and information for older buildings about specs for windows, walls, etc. So yeah, we'll kind of run through in the examples for the calibrated and existing models. We'll kind of run through where you can get some of that, and some of that was yesterday. Looking at the historic data and stuff of like when a building was built. I can point you to a few things. CBEX has some decent data about age of buildings and type of construction, and some of it is kind of localized. So if you work specific in like a city or municipality, it might be a little bit easier to find some of that information. But yeah, we'll touch on it a little bit later today. And then if there's further questions, we can certainly talk about that. So.
Okay, great, thanks. And please, as you have questions, please put them in the chat, and we'll try to watch for them. So next section, we're going to talk about a net zero design project. And specifically, this is a new dormitory at Williams College. They were looking to about 15,000 square feet in Massachusetts, and they were trying to go after International Living Future Institute, or ILFI, zero energy certification for that, which is quite aggressive. But so this is a very challenging project, but they had made a decision early in design to not just the design team, but the owner to go to zero. So they were having where they didn't want to have any net increase in energy use on campus, including the new building. And strategy, the residence was going to be net zero, and they were going to have a deep energy retrofit on the existing building next door. So the energy budget, and what are the goals and priorities? What do they want to achieve? How will they achieve success? Those are the metrics. How far do we want to get? Those are the targets. How are we going to do that? That's the strategies. And how are the opportunities to challenge or impact the goals? And how will we monitor progress, not only during design, but afterwards? There also, we talked a bit about site versus source energy, and site is what you measure at the utility meter, but source includes all the activities from mining, transport, power plant, and transmission losses, all the efficiency losses through the process. So source energy is generally 2 or more times the site energy for the building. Is actually higher than 1 also for natural gas, because there's pumping and losses with pipelines as well. So if we look at some of the conversions, you'll see these electric grid purchase, the ratio, these are for US, source to site depends on where you are. And so you have different numbers for there. So you see natural gas 105, electricity on site, because on-site solar or wind, obviously there's no or small losses related to that, and you see different conversion factors for that. So here's some example of site to source energy. You have site energy, which is just at the utility meter where the little electric spark is. Source energy is that plus what happens, transmission losses, and what it takes to convert whatever fuel it is into power for that. So it's often, as you saw, US average 2.8. Energy costs, on the other hand, are what it costs to produce that energy, and that includes all the costs back for that. And you often now see that there's a different cost from the production to the local delivery for that, and because they have to maintain the power lines. Greenhouse gas emissions, the carbon side of things, we have to look at what it takes to produce the fuel to begin with, but also what happens at the power plant. And so those are added up. So good to understand that. So if we look at some of the initial results for this, we started off baseline with steam, and there's the ASHRAE baseline, the code version. And then looking at some of the options for that. Also, there was some heat savings due to fuel switch from the steam to a air-to-air heat pump from 80% efficient steam to 2.50 P. So you see automatically we're doing better from what could be expected. And then you move on to some of the options. There was envelope, natural ventilation, light and equipment reductions, VRF and dedicated outside air, fan coil units, dedicated outside air, and a ground source heat pump, and solar water heating. Now you see all of those individually have options, and together, as you see on the right, we are getting to the target. The target was about enough to be offset by a 5,000 square foot PV array, about 75 kilowatts. So here's the budget. If they're looking for the area, they had trouble getting it on the roof. There just wasn't enough space to get the mounted on that particular roof. So the that becomes part of the difficulty here. Baseline design you see is the black line in the chart on the right, but the target performance requires a high performance envelope, HVAC, and lighting if you're going to offset that and being able to go to about zero. So there are several tools out there. PV Watts allows you to do some quick calculations for that. Homer, Helioscape, and then a number of the building energy modeling tools have PV capability as well, so that you can get more accurate tied to that. Rhino and Grasshopper have scripting for detailed analysis. These and some of the other tools will take into account overshadowing. So the equivalent first cost net zero energy building, this shows what the cost differentials will be. First, we're starting with hot water alternatives and looking at those. And you see the shaded areas, the additional cost of PV, trying to take it to zero in that case. HVAC alternatives, you see the baseline, and then 3 and 4 are getting there toward the end. Glazing, an option there, as well as wall alternatives. So you're seeing savings for the PV by downsizing or making everything more efficient as you're going along. So throughout this particular project and throughout any project, you really have to be doing continuous coordination, doing research, looking at options based on the locale, what will work. So you see in concept, we're looking at doing the research and schematics, showing diagrams of how heat flows might happen, solar angles, all sorts of various pieces. You see both the summer and the winter solar angles plotted on that. And when you're moving into schematic, you're doing continuous modeling and feedback as options are being tried by the design team. You're trying to look at what can be done and providing feedback on whether that's going to work or get to the goals for that, and that's really important. By design development, you're doing deep system dives. You're beginning to look in detail for particular PV. How many actual panels can you put on the roof? What are the kilowatt hours that you can get from that? And so beginning to look at these systems, whether it's PV or HVAC or other options as well. For this particular project, the level of effort you see wasn't a lot. So there was about 2 weeks, 1.5, 2 weeks for concept, another 2 to 2.5 weeks for schematic, and then 3, 4 weeks for design development, 100 hours for construction documents, and a little bit of time, 2 weeks for post-occupancy. And you'll see some of that change depending on where the intensity of the simulation is. So this was some schedules. So they were looking at, so this is a dormitory, often is very different from other things, and trying to look at occupancy, lighting, equipment, and how it might be different. So there are models for that. So there's dates when there's nobody in the building or very few people, and then they have again So you can see how that would vary. They also show, the schedules are basically 100% occupancy throughout the day, but much lower lighting and equipment levels for those particular cases. So this is an example of trying to track some of the assumptions, showing specific equipment. The more specific you can get, the more accurate you're going to be. So washers and dryers and how often they're used and their consumption. Computers, 30 people in this building, computers, clocks, phone chargers. You see getting very specific. Miscellaneous equipment. So you're beginning to see real data, not just watts per square foot. We're seeing the actual consumption for the year. This becomes increasingly important if you're trying to do a zero energy or zero carbon. You need to know exactly what's going on for that. Service hot water, how many showers, how many gallons, and what is that going to mean in terms of water use, but also hot water. And then once they started looking at it, when the initial design or initial look was done using PV watts, which doesn't do any shading look, but then they realized that the building was going to be surrounded on the south side by a number of pretty large buildings, so that they were going to lose about 7% of that, not large building, large trees. So it's important to understand the context your building's in, not just assume it's standalone on the site. Now, they weren't going to, these are mature trees. They weren't going to cut them. They're actually providing some shading of the building as well, helping with that. And so they took this reduction of 7.3% they took that and used that moving forward to make sure that they weren't over predicting what could be done. So this is looking at 25-year production. You'll see there's a buffer about 5% to make sure they still meet that. About 0.6% degradation in performance for that. And then we need a minimum of 17% buffer to maintain that net zero energy performance over the year. So that is so you're seeing the sliding degradation. Another thing they looked at was the impact of future weather. And I mentioned for Washington, D.C. that we're seeing reduction in heating degree days, increase in cooling degree days, but efficiency on cooling equipment is quite a bit higher than most heating systems. So what you'll see is a net reduction in much of the temperate climates for the world. So that is what we're seeing ongoing. I see a couple questions here I didn't catch. Kara asks, are each of these compounding? This was back on the chart that was showing natural ventilation and pH envelope and VRF. And yes, Kara, they are compounding. They're not individual in that case. They're a combination of starting with reducing loads and then efficiency of equipment and systems, and then finally PV in that order. Let's see. Jose asked on slide 230, where do we get the, it's actually 231, where do we wattage and consumption data for these? You see the data sources on here from various options, and some of these are cited in the references at the end. So let me go back to 234. Okay. So once we're in construction documentation, we're getting ready to build, we've got most of our assumptions there. So what are we trying to look? From what we can tell, we're only going to generate about 129 kilowatts of peak power for this. And so to be able to meet some of these schedules, what does it mean we're going to have to do? Set strict set points or relaxed set points to be able to meet these. So this accounts for the reduction, and the 25-year is based on the warranty data provided by the solar manufacturer. Moving on past construction, we're looking at the as-built model. Now we have to basically go back and test all the assumptions we made. So we might do a blower door testing. Interestingly, here in Washington, D.C. and in Virginia, next to Washington, they require blower door testing on all new residential projects. There is a maximum limit on that. But for commercial buildings, you might be looking at commissioning reports, test and balance, and approve submittal data, so that you're now looking at actually things that were installed. If you're trying to look at operational verification, utility meter logs and sub-meter data, so trying to look at various things. So there's an example of a submittal for the triple pane insulating glass unit and how it's actually, what its actual results are for the particular window that you have, because they will vary. Center of glass U value is often quite different depending on the size of the other. So you may have a pile of cut sheets that you can pull information as well as a record set. So changes in the as-built model, maybe there have been changes to the interior exterior lighting, likely increases has been my experience. Air leakage, you have to make an assumption about air leakage. It's about quality of construction for the most part, and you really don't know until you do something like the blower door test to be able to look at what's actually going on. You get variation in the window, SHGC and visible transmittance as you get to specific window, specific glazing options. Fan power on the dedicated outside air may be higher. Domestic hot water may be higher. People may want to take longer showers than you're assuming they are. So we take that into account, and then we start looking at the monthly energy consumed and generated, and seeing we have a generation deficit you see in January and in February. So we're not producing as much as we need. It's darker, so we're not getting as much solar gain. But then by March, we're beginning to get surplus all the way through October. So the overall idea is that that surplus would be higher than what's needed to offset the others. If we're trying to do a compliance project, number of things for there come through with specific operational practices that are that are being recommended for the facility. And maintenance is, what is a periodic maintenance? We need to be monitoring energy use continually. So if we see any significant changes in that, we can, even some sliding in that, we can look to see what's happening. Retro commissioning, regularly checking that all equipment is working as planned, and relaxing space thermostat set points a bit so that people that want something that's maybe not quite as controlled can do that. For the students that are going to be occupying the building, some basic explanation of what's going on, getting buy-in from the people that are operating the building in the building is really important here. So talk about natural ventilation, when you should use it, when you shouldn't. Shower time, minimizing shower time, not trying to take 30-minute showers for and just from an energy aspect for that. Laundry practice, elevator usage, lights and electronic equipment use, and what are best practices for all of that. And in this case, there's a kind of a self-guided tour that's been produced by the architects that explain what are all the best practices for that. So for this, the idea are, what are the appropriate questions to evaluate and how to do them with building energy modeling, and select the approach, what's appropriate tool, and input sources, alternatives, and where are you going to be able to update that. Implement a QA/QC process, provide confidence in the results, effectively work the design team, and communication again is key. Understanding the architect, engineers, and the owner's perspective on all this, and be able to provide quick feedback for that. And also develop a plan. What are you going to do at each phase, and what's your schedule and level of effort? So this is some of the learning objectives that can be done for that. I'm not going to take time here to do that. Look at the questions. Sean asks, is ERV degradation significant? Sean, it can be. I've seen a case where a particular building was trying to go for net zero, and they the installation of the filters around the ERV basically was blocking filter access. And so the filters that were in place were the original filters. They'd been there for over a year because there was no way to get a new filter in or get the old ones out. And they lost about 15 or 20% of the ERV effectiveness there because increasing the static. Jose asks, does ASHRAE have commissioning and retro commissioning best practice templates manuals? There are actually guidelines for that, and there's a standard for commissioning that ASHRAE is working on right now, but there are already guidelines for how to go about commissioning a building. And Sam, do you want to chime in about WFI or?
Yeah, I mean, I guess it's sort of out of the scope of what we're going to talk about today. I think certainly, you know, for projects, making sure, you know, the dew point is outside, like doing a WFI model to figure out where, you know, dew point will fall and where your, you know, vapor barrier falls, I think is critical. You know, a little outside, I'd say, of scope of what we're talking about today, but.
It is, but I think if you're in a situation where you're worried about moisture penetration,
Yeah.
WFI can be a tool to assuage that. I know some of the building energy model interfaces have tools to be able to show you where on design conditions you can expect to see condensation, and you can adjust insulation levels to try to make sure that's not in the middle of the wall. So that's kind of a key thing to understand there. Yeah. Luis says, thanks, he has to go.
Sean asked a question about ERV degradation. You know, yeah. It depends, in my experience, it depends on how well it's maintained. So certainly, you know, wheel type, you know, heat recovery units, they certainly get clogged, and they get, you know, the motors kind of get worn down and all that kind of stuff. As long as they're maintained well, you usually should, you know, not see much degradation on them. But again, I tend to find for existing buildings that there's always going to be a degradation factor applied to the effectiveness or, you know, the efficiency of a compressor or something like that. There's always going to be some degradation. So, and some of that is, you know, there's, depending on the type of equipment, it might be a few % a year over the course of a lifetime. So.
Sure. Tiana says, considering that occupants may not follow operational practices set, should the building be modeled take that variability in consideration? I think that you can do both and look at the sensitivity of that. If you're expecting that the students may do 50% more showers and use more power, try a model with that and see what the impact is, so that you're not making the assumption to a T, as you say. Mark asks, do any of the packages you cover include hydrothermal modeling? And Mark, no, this is really just an introduction to building energy modeling. We don't cover some of that detail of there. As you said before, WFI is a great tool for that, and I know there's training available for that as well. ASHRAE also has a standard 160, which deals with hydrothermal modeling, particularly from the weather data standpoint. Okay, so move on here. So Summary for this particular project: goal setting, definition, net zero, critical to this. That gave a target for that everybody was working against. But as Tiana said, operations schedule, plug loads, the uncertainty related to those is really key. Infiltration as well. You're making an assumption about construction quality and how well they're sealing holes, and also weather as well. As we talked about that at the beginning. Renewable energy is a bit of a challenge as well, and often you'll need to use a separate tool to be able to do that, to accurately estimate energy production and making sure you account for degradation. Don't just take the first year production for the whole time, and they did a good job for this particular project, making sure that they were still going to be net zero at the end of the warranty period. Again, communications, tracking all your assumptions, making sure you document it, so anytime anybody asks there, you can say, oh, that particular model includes X, Y, Z. These are assumptions. These are based on data on actual equipment, or however, whatever the question is. Again, working with the team, continuous coordination for that. So that's our zero energy project. So we're going to go through an example of compliance and green building rating on a couple projects for that. So before I go on, I see a couple questions. Do you usually give a safety factor for the building model calculation, make sure the building makes the design energy goals? I think let's work through the compliance, because I think that'll help clarify some of that going on. And Jose says, is a common practice to derate HVAC equipment for efficiency performance. And we're going to cover a bit more on HVAC equipment and modeling of that this afternoon. But yes, it's not just equipment performance, but also the efficiency at various conditions and not full load. Anything you want to add, Sam?
No, I think there's two things to consider there. One is yeah, performance over all of the operating conditions. That's kind of one thing. And then in terms of derating the efficiency of the unit for age or maintenance is a different item when you're looking at existing building, calibrated modeling, for example. So we'll touch on both of those. So.
Okay, great. Mark's.
Keep moving, Drew. We're going to run.
Yeah, I know.
Great questions, though. So what did Mark? Oh, there's one more. Yeah, for blower door.
Yeah, Mark asked, you mentioned a blower door test. You have a target ACH 50 value one should strive for. There are targets out there in the market. I can't tell you what specific one was. I believe there are targets in 90.1 at this point, if I remember right.
Yeah, there are. And there's also, that one specifically was looking at passive house as the metric, which passive house has, I think it's 0.6 air changes at 50 pascals. So ASHRAE is obviously a lot less stringent than that, and it's individual assembly.
ASHRAE is above 2, I believe, at this point. Yeah. But yeah, passive house is incredibly tight, well-built construction. Okay, let me keep moving. We're already an hour in. So compliance. The concept is we start with a proposed design, and its performance, whatever metric you're using, has to be better equal to the standard design. The proposed design is actual design. There are some modeling restrictions, so you can't try to make assumptions that you're better. The standard design is similar to the proposed building. It'll have the same sort of shape and everything else, but it may have a limited number of, wall area, as Sam talked about yesterday. Standard constructions, lighting, HVAC, all per the baseline standard. So some of the metrics, if I'm looking at 90.1 or IECC, the metric will probably be cost. So as long as the annual energy cost for my proposed design is better than standard, I comply. In California, it includes that time-dependent value of energy that Sam talked about. So it has both an energy cost and a source energy aspect for that. So again, modeling both sides of that equation. So some of the motivations for doing this, your design, you may want to have more windows and you won't comply with prescriptive energy code requirements. You want to do something that's different and trade one area performance for another. You want to do green building certification, or the owner has a target or a policy for that, or we're trying to look at energy efficiency incentives, and we'll talk about several of those going forward. So the typical process, we create a model of the proposed design, make a copy, change inputs to run that baseline design and calculate and document savings. The good news is this part of creating the standards design is actually automated by a number of software tools. They make it easier for you to do it. They'll basically take your model and create a standard design model for you. So here's an example of compliance. It's a 480,000 square foot dormitory in New Jersey. They're not looking for certification. Their objectives are to get LEED points. They also have university design standards, their requirements for energy reduction. In New Jersey, there's a pay for performance incentive, and they're trying to do code compliance, but it's not in scope. So they're using it to track energy performance for that. So we've got 4 different metrics we're trying to track. And so for LEED, we're looking at LEED Gold, energy design standards, 20% reduction below the Appendix G 2013 of 90.1. New Jersey pay for performance is looking 15% minimum energy cost savings beyond 90.1 2016. So there are adjustments there for that. And then finally, the New Jersey Energy Code just says better than baseline, and it's using 2013. So if you see there, we got 90.1 2010, 2013, and 2016, but with some amendments as well. So we're looking at various baselines for our standard design. So start documenting that. The ASHRAE Appendix G, beginning to look at that, you see 2010, 2013, 2016, and how even the climate zone changed for that, and what the requirements for the walls, glazing, roof insulation, lighting levels, and system efficiencies depending, and you do see some variations. So to do this sort of project, big project again, 480,000 square feet, so a lot more hours associated in collecting information. And so you see a couple weeks for concept, up to 4 weeks for schematic, of up to 5 for design development, 3 for construction documents, another 3 during construction, and doing the incentive applications. And this takes a lot of, it can be 6 weeks of work to do that. We'll explain why. Trying to read questions. Jingwen, it says, do you know the source? How do you know the source energy? Where can you find that? That's actually published often by the utility, or you can use some of the metrics for that Sam talked about yesterday at the utility level, but also the regional level for that. Let's see, Sean says, have you had the need to review baseline models generated by compliance software? Is the code being applied appropriately? The good thing, Sean, is most of the tools that do that baseline provide that model so you can review to make sure, and you can make changes to it if you don't agree with what it's done. And Keith asks, what staff is that for? This is for the, I would, I guess, call the energy analyst, the person doing the simulation work. Keep moving. So the level of effort, you'll see, the baselines, we've got baseline through schematic, pre-schematic, design development, and then in construction documents, we add the others to be able to look at that. So the objectives for pre-schematic, characterizing building use, getting envelope performance goals, set site intensity use goals, and opportunities to meet the DSM, design demand side management. Energy efficiency measures and tracking where we are on lead points, performing lifecycle costs at the schematic level, design development, what are the controls and operation alternatives, again, tracking DSM and lead points, construction documents, review, making sure as we're going through construction documents, making sure we are on track for that, again, tracking points. And then at that point, testing whether we're still going to be eligible for that that incentive. You see, at this point, we've got 3 baselines we're working against. By the time we're in construction, we're doing all of that, where we're beginning to pull the various pieces together. So if we start to look at this, initial results, annual site energy consumption on the left, our baseline and our proposed design. So we're looking at 21% savings of the for the building there. For that's energy. If you look on the right, it's utility costs, so a little bit less so for that, but we're still getting energy savings versus the baseline design. And then checking throughout design, where are we for that? 75%, are we still on track? Construction documentation, as we get more detail, being able to have that. We're seeing a little bit of change, but we're still pretty much staying on track for that particular case. And then when we get to the incentive submission, you've got to calculate what the incentive might be, work with the incentive organization, in this case, the New Jersey Office of Clean Energy, and they have to review and ask questions. You resubmit, revise, resubmit your calculations, and then they get reviewed one more time and approved, and you provide as-built models for that, so that you can see in this case they're looking at incentives that are quite like $1.50 a square foot for that. So I think I'm going to forego this, but here's an example you might want to look up if you're trying to do something, and do it for your locality, not just necessarily for New York City, but what is the energy code version you're looking at? What is the baseline for lead, and are there incentive programs locally for doing better than the baseline? So there's an example for 2 links there. So Sam, I'm going to hand it back to you so that you can go on and talk about HVAC.
Thanks, Drew. Let me figure out which screen I'm showing.
Under sharing.
There's lots of screen options. Does that look good to you, Drew?
I've got, yeah, there you go. You got it.
All right. Well, thank you. We'll run through, there's several examples here of getting much more into the weeds on HVAC modeling and the data that goes into the background, again, for modeling different kinds of HVAC systems. So we'll run through probably for another, I don't know, say 35, 40 minutes, and then we'll take a break, and then we'll finish out for the day. So, sorry, my screen is still being. All right, so one sort of major, challenge, I think, that a lot of modelers have, and particularly if you're starting out and you haven't done this a lot, is, you might get a set of plans that has, HVAC system, and you input the numbers, but do you actually know, do you actually know if the system is responding as it will in real life and in operation? So, there is a good basic fundamental requirement of HVAC systems, and I'd say it's the biggest learning curve when you're starting modeling. And even today, I still run into, projects where we end up seeing sequences and things that are, very difficult to simulate, and it might be hard to understand, how you kind of translate real life data into modeling data. So a lot of this is going to be looking at, what does it actually take to, model HVAC systems correctly. So we'll run through all of this, and we hit a little bit on this yesterday, right? That's kind of like the 30,000 foot view. Today, we're going to get into the weeds on a lot of the stuff that we talked about yesterday. So again, starting here is how do they work? But, in some cases, the model might not be exactly one for one in terms of how you're going to say it operates in real life, right? It's going to be it's a modeled version. You're doing a mathematical model to represent something that's going on in real life. So again, important to understand what the difference is of how certain systems are modeled, how we take those design inputs and change them into model inputs. That's kind of a big lift. There's a lot of mistakes and errors that happen when that happens. Understanding your software, which we talked about yesterday, can your software that you're using accurately model the system you're talking about? In some cases there's workarounds. In some cases you might want to make sure the tool you're choosing to do the model, for the specific application can handle what you're trying to do. And then understanding if you're going to get the right outputs, right? I mean, that's also critical to be able to check your models. So, and then you want to know how to actually use those models, right? So we've created a model, we've got an HVAC system that's running, but what does that actually mean in terms of helping a design, evaluate a design, or helping a design team choose a HVAC system, or update controls for an existing building. So we'll look at some examples of that as well. So again, you can use this to look at systems, efficiency changes, and the amount of detail that you're going to put in here really depends on the objective, right? If it is an HVAC system selection that you're looking at to answer with this model, right, you're going to put a lot of effort into the HVAC system. But if you're looking at lighting system change and it's a pretty basic HVAC, you're probably not going to spend a lot of time there. So level of effort is very important to keep in mind as well. So again, there's a lot to go on here. Like I said, this is the biggest, I'd say, hurdle and lift in terms of creating an energy model, is getting the HVAC system set up correctly and operating correctly. So, and this is something you will continue to learn as you do more and more modeling. And I don't think you will ever stop learning, because new HVAC systems are changing. We're getting different control schemes that are happening, different systems are coming to market. So there's always place to learn here as well. So we'll do some examples that are going to be some architectural ones, looking at energy consumption, maybe HVAC type, control schemes, or maybe some different code requirements. So what does it actually look like? For example, if you're doing an architectural alternative, right, in this case, you don't really care what the HVAC system is. You want to make sure that it's realistic and representative of a typical system, but you're not going to spend a ton of time. You're probably going to build a baseline code HVAC model if you're looking at changing out curtain wall, for example. If you're looking at, true estimate of building energy consumption, then yeah, you're probably going to get into the details on the envelope, the lighting, the HVAC, everything else that would affect total building energy consumption. So that might be, a much more detailed level of model. For comparing HVAC system types, in this case, you want to put enough detail in that you can actually make reasonable, judgment on whether or not one system is better than the other based on the results of the model. So again, particularly if you're looking at fuel switching, which is, in electrified buildings that we're seeing a lot of these days, you have to be very careful about, where you spend time for these as well. Making sure your utility costing is correct is very important, in addition to making sure you're modeling the HVAC system appropriately. And we'll talk about, what that looks like. If you're optimizing, actual specific control sequences, then yes, you're going to be spending a lot of time making sure that your fan controllers are set up correctly. If you have resets in place or static pressure resets, that they're actually, operating as intended. You're going to be looking at hourly data, right? So you're going to be making sure that those are very tight. And then for code, you're really looking on a baseline system. It's a set of rules, right? It'll tell you exactly how to build your model. And it's a good starting place to learn, kind of all the other pieces. But so again, you're going to choose the approach based on what you're trying to answer, right? And this is the first question you need to ask yourself. We've said it before, we'll continue to say it, that framing out what you're trying to answer will help, inform how you actually structure your model. So we're going to look at some examples for, efficiency measures, like what that actually looks like in terms of capabilities of softwares, how much accuracy is actually required, how to present results. We'll continue to look at that, because again, making sure you can clearly present the data and present the findings to the appropriate audience, is a very key part of being able to effectively do an energy modeling, project and support that role. So what could, for an example for envelope, if you don't have an HVAC system, for example, so you have 3 different facade options, you might have, again, 3 different HVAC options. And, again, this might be sort of a scatter shot, right, that you're doing, multiple sort of parametric runs to figure this out, but you might be running each one of those facade cases with each one of those HVAC system options, and maybe a couple different chiller options, right? So the level of, how much you're getting into really could, like how early on you are and what the questions are that the design team or the owner is looking to answer really could, broaden the scope of the model. It could be very focused. So we'll look at an example specifically for this one of what happens. We showed this yesterday. So what's the impact of window area on energy use? So what is the HVAC approach here, right? You don't have, maybe let's say we don't have any information on the HVAC, or maybe we have an existing one, but if you think about it, the characteristics of this HVAC system will impact, what energy use. If you put an all electric in there, heating and cooling system, certainly that will look different than if you have a boiler and a chiller. So how do we do that? First, start from the basics, make sure your thermal zoning is set up correctly. We'll look at system selections, and then run through some controls and setups. So first, for thermal zoning, we talked about it before, we'll talk about it again. Very basic at this point. If you're looking at envelope, right, we don't really need to get into the weeds of what's going on in the perimeter versus core of the building, but we do need to separate them thermally. And then if you're looking at system type, again, we don't have a system here, but as we mentioned yesterday, let's go to 90.1 Appendix G. We'll figure out for this building, which is this non-residential, less than 25,000 square foot, we're going to pick a package single zone. In this case, you have 2 choices here. You could do air conditioner that will have a furnace, or you could have a heat pump, again, all electric option. So in this case, selected a heat pump for this, 1 system per zone. So you'll have 1 sort of heat pump, 1 thermostat per zone, and you're set up as a constant volume system. So again, you could use other baseline systems for this. You could set up different, HVAC systems. If you had a real system, you could obviously use that, but in this case, there was not a selection. And so what else do you need to go find? Again, we talked about this yesterday. We'll kind of get into the weeds a little bit more in order to specify this HVAC system, right? So first you need to get cooling efficiencies. So again, let's go to 90.1. We'll grab the EER and the COP values. You could also go, 189 or the AEDGs if you want to be a little more aggressive on how efficient the heating and cooling systems are. And for reference, let's talk about EER for a minute, because I think there's some confusion about how you translate an EER value into a modeling input. And I think it's a very critical one. I've seen a lot of errors made for it. And if you're going to submit a lead model or a compliance model, you certainly will get a comment on this from the reviewer. But the EER is, a rated tested condition at 95 degrees with 80-degree dry bulb return and 76 wet bulb return, right? So it is a fixed tested condition. But in order to get a model input, you need to know a lot of things. You need to know the capacity of that coil. You need to know how much heat's being produced by the fan. And ultimately, you need to know the specific compressor and condenser fan power, right? So those items will help you remove basically the supply fan, right? Because EER is inclusive of a total input power. That input power includes your supply fan. So when you translate that to a model, you actually need to take that supply fan and the heat associated with that supply fan out of your calculation. That will help you identify the compressor and condenser fan power specifically, which is what you want to input for your model, right? So again, each software is a little bit different in terms of what they want. For example, in a DO2 simulation, you need to put in just the compressor and condenser fan power. If you put in the total ER, you will underestimate the efficiency of the unit. IES, for example, if you put in the rated EER, like the value on the left that you would read from a table, it will automatically do this calculation for you. It will deduct out the supply fan power and heat for you. So just make sure you understand how that works with the software that you're using.
Sam,
yeah.
before we go on, Jose's asking, will SEER and SEER2 matter as well, and how would you take that into account with the EO?
Sure. Yeah. So those are the newer efficiency ratings. So SEER and then SEER2, which is the one that's now showing up in the 2022 standard. So similarly, there is a rated methodology to determine the SEER or SEER2 value. What you need to understand is what the rating condition is and be able to extract the actual compressor input, so the input power for heating and cooling out of that equation. It's a little more convoluted because SEER is looking at a seasonal, it's over a course of several different outside air conditions, whereas EER is a single point. There are conversion tables. There's also a couple formulas that were, if you go back to the previous versions of the ASHRAE standard in 2013, I think was the last year they were published. There are some sort of normative equations that will help you convert the SEER or SEER2 values into a appropriate like cooling input power or heating input power. So yeah, the other thing is to go to the manufacturer and actually, when you get a selection sheet or a spec sheet from, Aon or Carrier, whoever it is, that you would look and see, and they now are being better about reporting compressor power input for heating and cooling separately. So you'll see it for VRF for sure. They've been doing that for a while, but on the rooftops and sort of this other packaged equipment, you'll now will see the compressor and the condenser fans isolated. So you might have to go, dig a little bit into the equipment. Otherwise, if it's standard and you're doing sort of these baseline, models, yeah, you might go back to the previous ASHRAE 2013 and use the formulas. And then Craig had asked, in the package single zone, is the fan heat exhausted or going across the coil? It depends. I think in this diagram, what we're showing here is that it's ending up in the box. So it's considered part of it's in airflow. So you'll end up having, whatever 1 or 2 degrees get added to your off coil temperature. So it depends where the fan's located. And the system, but again, most softwares will allow you to either put it in the airstream or take it out of the airstream. So if it's an exterior motor, you can take the heat out of it. Yeah, and so again, for EER, just following up on Craig's question of whether it's using gross or net, the rated EER value is net. That is just the rated condition. So it's already taking out the heat from the fan. So again, when you have to go back and translate it, that's the way that they do the test for them. So again, just makes it more convoluted for us, but and then continuing on with the same example, what about fan power, right? So we have a system selection, but fan power. So again, an easy place to go to look to get standard fan power or static is to look at the fan power allowances that are provided in ASHRAE 90.1. So there's 2 options for doing this based on brake horsepower or just general horsepower. I tend to defer to using the brake because that's the actual shaft power that's being consumed. You'll find a lot of manufacturers will actually be reporting brake horsepower as well. But there are, again, formulas here that will allow you to calculate the total fan power based on the CFM your system. There's also these add-on static pressure credits again. So if you have, high filtration MERV 13 or MERV 16, or, carbon cleaning or heat recovery, you get additional credit. So again, if you have those things, you would tend to include them as static pressure credits. Here, you get a little bit higher fan power. Again, just for reference on the fan power, the inputs that you're looking for into the model is you're putting in, the total fan power, electric motor in power, right? So depending on what data you get, you might end up with the brake horsepower, which you're going to calculate from your static potentially, or it might be a selection. That then needs to be accounted for, or needs to be translated into actual fan power itself, which is going to include the motor efficiency and then the total system belt efficiency. So again, once you have sort of a standard calculation sheet set up for these, or you can use the DOE compliance tool, will do these calculations for you as well. But good references to know. Again, when you get a data sheet from a manufacturer, you still need to translate that into a input into the model. And then what about other system characteristics? So for this one, when we're looking just at envelope, you might just let everything get auto-sized, and most softwares will have the capability. So they will run a load calc and they say, oh, based on the load calc, we need a 2-ton, cooling coil and a 1.5-ton heating coil, right? So you're going to set parameters around the temperatures that are being supplied and the space temperatures, and then the delta T will be how how your coils will be sized. You can also include oversizing, and I think 90.1 Appendix G gives you what you should be using for your baseline, and those are usually pretty typical in terms of adding safety factor. So again, there are easy characteristics to follow through if you're doing this just for looking at envelope. And so for this example, running those 5 individual zone heat pumps, you get cooling heating capacity. There's supplemental heating provided by the heat pumps as well. And again, depending on the type of heat pump and the climate, you might need to have an electric coil as supplement, and then calculated airflow. So, and then what about ventilation? So again, ventilation generally is going to be driven by ASHRAE 62, but it depends. If you're in a multifamily, it might be ASHRAE 62.1. It could be 62.2 if you're doing multifamily. But again, fairly simple and quick calculations, and particularly if you use the ventilation calculation sheets, you can come up with some sort of simple parameters. In this case, using occupant density and standard office, you can have a standard input for all your zones of 0.11 CFM a square foot of fresh air. So again, very simple, use it all for all the zones, use the same value. What about controls? So in this case, for this climate zone and this system type, you need to have an air sign economizer included. So, there's multiple, operating control schemes that would be here. So this is required everywhere except for sort of humid climates. But there's minimum OA that's basically during operation when you don't hit economizer conditions. And then you have sort of a modulating that's like when you're in between your sort of prime economizer temperatures for outside, and then once you hit sort of full economizer mode. So making sure you're, again, modeling sort of minimum code requirements as well if you're doing this type of analysis. DCV, again, could also be required by code, so this might be something that would need to be included up front, which again, there's 2 different ways really that softwares do this. They either do zone level sensor or a return level sensor. So again, they generally will have similar results, but again, if you have very, very wide variety of occupancy in a building, you would want to make sure that you're modeling this correctly, based on those higher occupant density spaces. So sometimes this gets translated as a schedule. Sometimes, the software will do is a CO2 generation per person in the room, and then that will, tell you whether or not you trigger your limits. So, and then you also need to set up, as we talked about yesterday, a fan schedule and cooling and heating set point schedules. So again, these might be very generic at this point if all you're looking at is facade, right? You don't really want to do anything crazy here. You kind of want to get through and make it quick. So And then what are the sort of things that you would look at if you were, doing QC? And we'll talk about, quality control quite a bit today as well. Is, look at your inputs, again, keeping track of all your inputs, check those against your outputs that are coming out of the model and make sure they're the same. A lot of times you might see some translation errors, so it's a good place to look for that when you haven't potentially, input something incorrectly. Always looking at the results, making sure they're reasonable and they're in line with what you expect. And there's a lot of, ways to check, and we're putting these all out there for, for everyone to be aware that there's, kind of a 5-minute, 15-minute, 30-minute, and then like a detailed review. Generally, you're going to be doing reviews as you run through the project. You'll check system by system as you're building models. But again, it depends on the level of effort and kind of what you're trying to get to. So these are just sort of good references of things that you can check. I see a couple questions. Occupancy, Jose asked, are occupancy sensors used for DCV? Increasingly, yes, we're seeing OCC sensors being used for DCV, where you're using, the same OCC sensor is controlling your lighting, your VAV box minimum, and your outside air damper. So it can be that. I would say in terms of modeling, you're really going to be using whatever the software does. So you might be creating a schedule that mimics your occupancy, or some alternative where they're calculating a CO2 generation rate. And then Craig asked, for purposes of modeling, would you also include the zone air distribution effectiveness? Yeah, so going back to the, go backwards, right? Yeah, so if you go back to the calculation, this is just very simplistic at this point because we're talking about envelopes, so we're not really all that concerned about, how the HVAC system is set up and running. It's kind of a simplified version. But yes, if you were going to do this in detail, you would account for the fact that there might be a additional ventilation required for distribution effectiveness. So good question. And then, okay. Good questions, thank you. So what are things that you could do? Again, I'm going to run through others, and I'm not jumping in these. I'm going to run through all of these. So in terms of load inputs, things to check. I see a lot of errors around, the area. So one thing to make sure your drawings were scaled correctly and that you translated them correctly. I've seen a lot where, people that were new to modeling didn't look at the scale on the drawings and just started, copying them into the modeling software, and you end up with a building that is, a quarter of the size or 4 times bigger than it should be. So always a good place to look. Lighting power, plug power, again, for just, kind of high level, make sure that they're in range of what you would expect. People, general U factors for envelope, and again, in this case, you're varying the envelope, so those are going to be fairly critical that you're going to look at. Solar heat gain and window to wall ratio. So again, this might be a standard output, from your software that you get that'll have, like a zone level summary input that'll tell you these kinds of things. So most softwares will have a simplified output, or you can just look at the input sheets that came out of your software when you were inputting the data as well. And then on the system side, the sort of critical things, check your heating and cooling efficiencies, make sure that those are actually translated correctly from, EER and COP, total fan power and total vent rate. And then other things to check, make sure your end use breakdown is reasonable. Again, so based on the building type, this is an office. This is kind of a fairly typical breakdown where you have, 45, 50% of the energy consumption is plug loads and lighting. In this case, fans is a little bit high, but again, it's rooftop all air system, so that might be reasonable. So again, just make sure it's kind of in line with what you would expect. And you can compare that, say, for example, to the CBEX database. You could go look for typical offices, or Energy Star that has typical office breakdowns. Again, looking at monthly, make sure that you're not, blasting your cooling system all through, the winter time, and you're not, simultaneously heating and cooling in the summer. You could be looking at hourly. So again, looking at total electric demand and seeing what's happening. And in this case, it's electrically heated, and there's a lot of electric resistance for those heat pumps. So kind of makes sense that you're peaking out with your electric peak in the wintertime. And then this is another way to visualize the data. This is just looking at electric demand, but in a chart to look at time of day So again, it's kind of taking this linear plot and putting it on a surface plot to kind of see exactly when those are peaking, right? And you're seeing that they're peaking in the mornings during warm up in the winter, right? Which is when you would expect the system to sort of be hitting its peak. So, and then again, check the differences between the two changes. So in this case, we ran an example with and without daylight controls as, you know, just an example, and different window to wall ratios, right? So higher window to wall ratio, you should start seeing your lighting going down, right? So you're going from say 62,000. My pointer just disappeared, sorry. Right, yeah, so you're going from say 62,000 kilowatt hours a year all the way down to 42 with the increase in window to wall ratio. That makes sense. And if you turned it off, you should not see any variation in lighting, so that makes sense, right? So easy things to check for, you know, and subsequently, yeah, you're going to see changes in, you know, heating and cooling. Cooling should be going up with all of these changes as you're adding. Your heating generally should be going up as well because you have more heat loss through the envelope, right? So the results tend to make sense. And again, one other thing, you might go look at benchmarks, right? And so this is, again, checking consistency of data, making sure that what you've simulated is sort of in line with typical buildings in the same, you know, climate zone. So one place you could go look is the zero tool, which again gives you a median sort of building output, which they consider to be, you know, 87 kBtu per square foot. In this case, we're simulating just, you know, about 33 kBtu a square foot. So it gives you an idea that you're, you know, in that range, you know, close to 70% savings compared to a typical building. Again, you can also go look at the AEDGs. So again, for small to medium office, it'll give you, these are the zero energy ones and the 50% reduced ones, but it gives you an idea of where you've simulated compared to the benchmark from that guideline in different climate zones. So just another way to check if your performance is in line with what, you know, the data says from other buildings. So again, just looking, you know, this one ends up with 23 for a specific in Chicago. And so we're a little bit higher than that, you know, at 33, but just good reference point as well. Other things to do is to check that you're actually meeting heating and cooling load. So this is something I think if anybody's done any amount of modeling, you know that this is something that is painful sometimes when you cannot get a simulation to converge. So, you know, check the unmet hours, look at the zone air temperatures. You know, in this case, it's kind of, you know, doing setbacks and, you know, hitting through the summer. So other things just to look and make sure. And again, if you're doing compliance, that obviously will show up. And then do some, you know, checks on sizing of equipment. So again, you can kind of just do some benchmarks on this, you know, how many tons or how many square feet per ton and BTU per square foot and CFM per square foot to make sure those are kind of in a reasonable line with HVAC design. So, and then one other thing to do is to look at the average, you know, efficiency of your delivered cooling, for example. So if you know that it was an 11 EER system, you might go look and sum up the total cooling energy that has been, or the total cooling that has been delivered, and divide that by the electric of your, you know, compressor to see where you actually got in terms of a, you know, an efficiency of your total cooling system. So again, you're going to be operating a lot of hours that are not at that design condition of 95, right? So you expect, you know, if you were to do this check, that your EER would be a little bit higher than the rated condition at 95. So. Same thing on the heating side. So in this case, you know, the heating COP is a lot lower, and the reason being there is that you have all this supplemental electric resistance heating, right? So again, the controls may dictate that you need to turn those electric heaters on, you know, whenever it hits, say, 20 degrees Fahrenheit and below. Good thing to just double check and make sure the manufacturer can, you know, that the equipment can operate down that low based on the manufacturer's data. So then there are some standards for that in 90.1 as well. Other things to check, you know, look at total airflows and make sure your ventilation rate is as expected, right? So we had calculated 0.11. In this case, the model is input a little bit more. Sometimes that's when you auto size, it gets a little bit off. But other things to check, the CFM per person, that's sort of in line with a typical office. You see anywhere from about 17 to 25 in a typical office. And 10 to 20% of total supplier as fresh air is pretty reasonable. And then what about communicating results, right? So you might be showing some data tables like the ones we've shown here. You might be looking at some sort of surface or surface plot too that's showing lighting energy is basically going down. But one good thing to show when you're looking at sort of a parametric like this is it might be helpful to visualize the data to figure out where the minimum is, right? Because as you start getting larger window to wall ratio, in this case, your heating, cooling, and fans are going up, right? And that's subsequently not being offset by the daylight controls. So your minimum in this case actually is not 10%, but it's, you're getting enough daylight harvesting from lighting at 20%, for example. That's your minimum sort of EUI. So again, it's a good way to visualize data. And then you can show that same without daylight controls. If you did not do daylight controls and the same window to wall ratio, right, you can see what the delta is between the EUIs. And then in terms of documenting assumptions, again, this is just kind of a simplistic version, but if you look at the BEM Cyclopedia, the reference, you'll see there's a couple different ways that people present this data. But again, putting in enough detail here that you can go back and you can justify the results, right? So, and if someone is going to review it, that they can review it thoroughly, right? That's also helpful. I see there's a couple questions. So George asked, considering the input data for HVAC, is there a rule of thumb data library from shared yield simulations? That is a good question. I don't know if there's like a database where people dump their data. I mean, we certainly keep track of it in-house, and so we use, we've got a database of, I don't know, hundreds of models, real data from those that we use. I don't know if there's anything publicly available that has that kind of data. Drew, do you know of anything that would?
No,
Yeah,
not for HVAC. That's kind of a challenge, but that.
Yeah. I mean,
I mean, there's some research projects that have been trying to do that, but it's based on a lot of assumptions.
Right. Yeah. I mean, I think there are case studies and things that have been presented, and you can go dig individual data points out, but I think it's hard to get a fairly large, rule of thumb library. I would certainly love to see one. Yeah. I mean, there are some books like Kara mentioned, the HVAC equations and the rules of thumb. To be honest, I still think that's pretty out of date. And, we do a lot of comparisons against those, particularly if you have sort of more complex HVAC systems, you're really pushing the limit on some of those rules of thumb. But that's a great place to start, is that the HVAC equations, data and rules of thumb, the Bell book. If you don't have anything else, it's a perfectly good place to start. I think once you get into real design, you'll find that the numbers don't really line up. And then Jose asked, is there an EUI reference for older buildings? Yes, if you go to CBEX has many, many years of data, and it'll tell you when the building was built and what types of systems and where they're located. And you can slice and dice the data to find all kinds of EUI. I will say there's rabbit holes you could go down with CBEX, but there are some simple tables that are sort of at the front end where you can go back and look back a few years or many years and get data for those. And then also the 0.12 CFM per square foot, is that standard practice for OA? That is not standard practice. I'm just saying for this specific office, that's kind of a number where we end up seeing like 0.1 to 0.3, 0.1 to 0.13 CFM a square foot is kind of where we end up seeing ventilation for offices. But certainly that will depend on, the density of occupants and, the type of space and how much different space types that you have within the building. So those are just kind of rules of thumb, which again, may be good, may not be good. Again, as Drew mentioned yesterday, the models are generally, it's garbage in, garbage out for the most part. So making better assumptions, better calculations. But again, it is a big set of assumptions that we're putting into these models for the most part. So as close to reality as we can get would be where we want to be. So next up, we'll run through a comparison of doing different HVAC types, right? So the first one was just looking at one HVAC system and using that basis to do some analysis on daylighting and facades. In this case, the question here is, what is the most efficient HVAC system type? So let's say we have a building and we know the characteristics. We've got envelope and so this is kind of an example of an early design. You might have a simplified massing, and the designer has 3 options on the table, and they're going to get pricing, and they want to know operationally what was it going to cost to operate each one of these systems, which one's more energy efficient. So you might have, in this case, a package single zone, package VAV in this case, and you have reheat that's going on, or you have a split VRF and you have a little DOAS unit that's providing ventilation. So where are you going to get data here? Again, you might have some basic massing, so some drawings. You might be getting in a little bit of code data, like for example, they might not have ventilation determined at this point. This is still sort of high level looking schematic design. So you might be calculating based on like what we did in the previous example of ventilation. You might be pulling manufacturers data because they might not have selected equipment for this yet. So you might have to go to each of the manufacturers and look through their websites and find the data. So we'll step through and look through all of these. So again, so what the approach here for doing a comparison on HVAC is a little bit different, right? You want to make sure that the load model is detailed enough, that you can answer the question of which HVAC system is more efficient. You want to have a reasonable and fairly accurate inputs for your options. So you want to make sure that you're capturing controls correctly and efficiencies correctly. And then you're going to compare like to like, between the two systems. You're going to change just the system characteristic inputs. You're not going to change anything else, just to make sure you have fair comparison between the different systems. And finally, at the end, always review your, review your inputs, review your outputs. So things to keep in mind as we walk through this one is that details will matter when you're doing this type of modeling, right? And the metrics will matter when you start looking at capacities and efficiencies. So early phase on, what are we going to have? In this case, you've got preliminary floor plans, elevations. Things you probably don't know is, you don't know how the building might be zoned on the inside. You might not, have a full HVAC system layout. But things you want to be careful about here, right, is that windows, obviously, we're going to have a fairly big impact. So you want to make sure those are correct. You want to make sure you have a good spec for that everybody agrees on the spec you're using for the windows. So that could be something that you need to, pass in front of the team and make sure everybody agrees on before you proceed with this exercise. So again, still subjective analysis here, but again, what you're trying to do is compare A, B, and C, right, 3 different HVAC options. So things that you're not going to have likely, you won't know the performance of the envelope. You probably don't have lighting. You don't have schedules, but you can fill in the data for a lot of these things based on the sources of data that we've talked about already. And then finally, what do you want to do? You want to get the right level of detail. So important things here, windows, as I mentioned, you want to make sure internal gains are reasonable for this type of building and your schedules are reasonable. And for most of these things, you can get pretty good, data. But again, the idea is document it, make sure that it's easy to follow up and easy to review. So again, we don't have a design for HVAC, and you want to be reasonable and fair in doing your comparison of these, right? You don't want to weight too much, efficiency for one system versus the other. So your approach here is to understand how they work, how your model is going to, the energy model itself will characterize these different HVAC systems. You want to go gather data. So again, going to manufacturers to get it. And again, in this case, potentially run some sensitivity runs, right? So kind of if you don't know what an input is 100% correct, you might run 3 different versions of that input, right? To make sure that you get kind of a spread of details and see how sensitive the model is to that specific input. So in this case, for a package single zone system, again, in this case, you're going to have 1 system per zone. You're going to have 1 thermostat. You will have separate heating and cooling schedules, separate fan schedules. This is sort of, I would say, the least efficient of our options. You have constant, airflow generally, but there might be characteristics where you have multi-speed or variable control. Again, that'll make a very big difference on how these systems are being, how much energy the systems will consume. You'll need to decide on heating source. So again, most commonly you'll have a furnace or a heat pump in this case, and how the cooling system is going to operate, right? So if you have single compressor, multiple compressors, are they unloading? Are they just hard starting? And then, as we talked about before, how is outside air being controlled? Is it just fixed, or is there an economizer that's actually operational? So this might be, the important inputs that you want to follow for dealing with a single zone system, right? You want to make sure your capacities, and again, you'll use the same capacities across all of your comparisons here. That's one thing you want to keep consistent. But you want to make sure you get the full load efficiency and the part load efficiency of your compressor system, both on the heating and cooling, fairly accurate. Again, there's some pre-packaged curves, which we'll look at some in some other examples. But if you have, real manufacturer's data, that's better to use in these cases. Airflow obviously wants to be, flow rate plus the control on airflow, fan power, and how you're dealing with outside air. So again, this is kind of your inputs. Here's an example of what you might be including as your inputs to the model and keeping track of. Right, in this case, you're probably auto-sizing stuff, which is good. You might be using default curves, following the basic economizer controls from code minimum requirements. So then you might be running sensitivities, okay? So the example of this would be, sorry, turning backward. So showing both EUI on the left, I apologize, and cost on the right. What is, the change if you have variable flow fan systems? So that's the sort of first one. And then what if you add, heat pumps on top of that? What does that actually look like in terms of your EUI and your cost, right? And so on EUI, you're getting a full reduction down the line from 43 down to 32. But in this case, the electric cost has this demand component to it, right? So actually, your low cost option, if you're looking at cost as the metric, would be just going to variable flow, but keeping it as a gas heating system. So when you're looking at a packaged VAV, there's a few more things that you have to look at in this case. In this case, we have a hot water reheat system. So you need to characterize the boiler as well, and we'll talk about that. So you also need to talk in this case about the type of VAV box, whether it's a fan powered or just standard box, potentially dual duct. Some older buildings that might be the case. And then the zone heat source. In this case, we have it as a hot water, but it could also be electric, right? Or you could have heat pumps. We're seeing some that are being able to produce higher temperature water that works as reheat. And then your main air handling unit likely will have a heating coil as well, depending on where you are climate zone wise. But again, you could characterize that as furnace heat pump or a hot water coil. Same thing on the compressors. On the cooling side, how is that actually operating? And your fan controls. So generally with these, you're going to get variable speed control because you've got, pressure dependent boxes that are running, and your VFD is going to run, based on the position of all of those boxes. Also outdoor. And in this case, you might actually have variable supplier temperature, right? So if you go back to the single zone case, you're probably not resetting supplier temperature. It's, packaged simple controls. In this case, you might be resetting, based on zone load or based on outside air temperature. So just some examples of some different box types. Again, things that you might see out there that you might need to characterize. The dual duct, I'd say, is probably, not that commonly used anymore, just because it's fairly inefficient when you're heating and cooling and then mixing. But most commonly, we're seeing, one of the three, the standard VAV that's got a reheat or a series or parallel box. So again, understanding what they're planning to do in the space, is helpful. If you don't have an option, again, using something that's more standard like a regular VAV box for this example will work. And then what about, how are you controlling your VAV box controls? So standard control, says that if you're in your deadband, you're sort of resetting your boxes to minimum, and they're staying at that point all the way down through increased heating demand, right? And then as your cooling demand increases, your boxes are opening up to meet that increased space temperature. When you have reheat on, right, you're actually going to be going the other direction, and you want to make sure that whatever this minimum airflow requirement is, it can actually push enough heat across that reheat coil to get a good delta T across your coil for reheat purposes. So alternative for this, again, a fairly common, I'd say most box controllers now are doing what's called dual maximum or dual minimum controllers, where at the low end, when they get to heating, they actually start kicking back up, and the box will open up a little bit more. Generally, it's hitting up to about 50% airflow under the heating condition when you have a reheat coil like that. So again, understanding the different ways you can do that, right? I mean, some of the older buildings will have just a standard controller that doesn't actually increase the box or open the box damper anymore when you get to heating. What about fan power and flow curves, right? So this is something, again, there's a lot of prepackaged curves that will come with the different software packages. So a lot of them are using, the reference 90.1. There is a fan curve that is in Appendix G. It's been in there forever. That basically follows this red line, right? That says that if you have a VAV system, that you should unload along that line, right? There could be ways to model, sort of model static pressure reset as well. Some systems will actually model, and some softwares will actually model pressure within the system. In many cases, you're just going to have to create a separate fan curve that mimics what would happen if you have a pressure reset system. So other things just to know. So again, in this case, it looks very similar, but we're adding for this VAV system, how are we controlling the supplier temperature? And we're looking at a little more detail in the fan systems, right, where we need to understand the consumption of the power consumption of the fan at different flow rates. So again, this might be examples of what you're putting in. Again, a lot of auto-sized. In this case, for that fan curve, you might be just using a default variable speed fan curve that comes out of the tool. You might be using the Ashray one. It just depends. So what does this look like if you wanted to check sensitivity-wise, right? So let's just look at a couple examples. The same thing. Energy use intensity and total cost. Again, using the same metrics, same cost metrics as we had before of our standard VAV system with 30% min. That's Ashray baseline requirements. The baseline also here requires a supplier temperature reset. So if we go back one, you'll see that includes a 10-degree reset, which is actually a little bit higher. Code requires 5. So in this case, the base model here is including a 10. The first run is taking that out and seeing what happens. So by removing that and doing a fixed temperature, you're actually increasing your heating pretty drastically, right? And so you're going up almost 10% on EUI. And then the other ones are looking at if you went to 40% min on your boxes, 20% min on your boxes, or 20% min and you added a condensing boiler, right? So these are the kind of things that you can do when you're looking at these HVAC system options. And again, looking at cost, obviously, there are no all-electric options that we ran for this since we had a gas boiler. And finally, we have a DOAS system that's packaged with a VRF or a VRV system, so indoor fan coils that are connected to outdoor condensing units with the DOAS. So again, getting a little more complicated. There's a little more equipment you have to specify here. One thing you need to be concerned about, particularly the type of equipment, but also what the software is capable of modeling, because there are different types of these systems, right? There's cooling only systems, There's systems that can operate only in cooling and only in heating, and then there's ones that have a simultaneous operation. It takes a lot more detail to model out the simultaneous ones, and some softwares do it well, some you kind of have to do it manually after the fact. But again, be aware that there are lots of options out there. So similarly, you need to understand what your indoor units are doing, if they're constant or variable. Ducted, non-ducted will change the static pressure of your indoor systems, so fan power will change. And then we're adding in the DOAS, which again is like one of the rooftop units we were looking at before, but you got to consider the heat source, cooling source, whether there's heat recovery, and the schedule of that unit as well. So inputs here, again, similar, but you have a DOAS that you're adding on top of that. So you might have, again, similar set of examples, inputs. So again, in this case, we're just looking at a constant speed DOAS that does not have heat recovery, right? So a couple critical things to look at that you're not doing that. And so what could this look like if you're doing sensitivity on this type of system? Again, you could have your base option, which is everything that we just talked about. If you added heat recovery, and in this case, the ventilation might be such a small portion of the overall flow that adding heat recovery actually doesn't do a whole lot, because you got to overcome the static of that heat recovery unit, and you're only gaining a little bit of savings by doing that, right? So that's kind of a good indicator that it's probably not worth it to do heat recovery. But adding variable airflow to your indoor coils saves energy. If you do longer runs on your pipe, you'll end up paying a penalty for doing that. Better controls on your evaporators. So again, that's a refrigerant control item. Or if you combine all of them, right, you might end up with some little bit lesser number, right? So again, just other examples of things that you could do in terms of testing sensitivity of how the system might perform under different characteristics that get designed later on, right? The idea here is that it's not a very big spread between the base and all the other options that you had. Yeah. So what sort of things would we look at? Again, we've talked about it before, but look at your end use breakdown, and then look at hourly controls and variables from your output, looking at total system performance, space temperatures, make sure you're meeting set points. So what does this look like that you might do this comparison, side by side to compare all three of them, right? So in this case, everything is being normalized on the electric side, all under kilowatt hours, and your heating is all being calculated as therms. So, looking at the package single zone, you're 354,000. The VAV is a little bit lower than that, and your VRF is a little bit higher. And one thing you might want to do is just look through at your cooling and heating and understand, and say your fans, can it be explained as to why you have a difference in cooling energy, right? Why is your package single zone and your VRF so much more efficient than the larger VAV system? Same thing with fan power. The VAV fan power number is substantially lower. Can that be explained? Good things to check, since we're not messing with plug loads and lighting, right? These numbers should be the exact same across the board. So you want to make sure that there's no changes. If there are changes, then there might be something happening in the model, inputs that would not be, that you don't want to change. And then finally, looking at your heating, can it be explained that the single zone is going to be more than the VAV reheat option, right? So side by side, it's sometimes helpful to compare and just make sure that you understand why you're seeing the savings or the variations that you're seeing. Okay, there's a couple questions. One is about BTU per therm versus kilowatt. Yeah, and this is just an example of a condensing boiler option. I think certainly there's other reasons to go down that, but generally you're getting at lower water temperatures on a condensing boiler, you'll end up getting closer to 90-95% efficient delivery. So again, depends if you have availability for gas as well, and what gas prices look like. So there could be a lot of reasons to go with condensing versus heat pumps or something else. And in this case, Jose had asked about initial first cost. Not for this one. This was just looking, again, that would be, I think, something you would like to include if you were doing an HVAC analysis. You would want to say, okay, what's the next step sorry, you would want to add the cost. So what does it actually cost to run each one of these systems for a year? And then you would want to look at the first cost. You'd also want to include maintenance. I mean, there's other things that, that you would put into this. I think this is just kind of it's a more simplified comparison, just looking heavy at the HVAC analysis. But yes, you would certainly look at payback and first cost and return. A couple other questions. Is ASHRAE guidance for modeling pool heaters? Good question. I'm assuming you're talking about indoor pool heating or outdoor pool heating. There are some, again, research papers and some people that have studied this in terms of heat loss from pools. There's a couple calculators that are out there. There's some nice ones. There's a firm out of Vancouver that's done this as well. I don't think ASHRAE has a specific guidance in the handbook, or actually I think it's HVAC applications. There is a methodology of dealing with heat loss and heat gain in a pool, because you've got to account for solar that's actually adding to your pool and whether you have covers and all these other things. So there are ways to do it. We have a custom tool that we've built. I don't think it's great, but it helps at least a little bit with that. And then Craig says, why wouldn't the DOAS VRF utilize less fan energy than the VAV? That's a good question. The choice here of the VRF, this includes the heat recovery piece. It also, there's, again, the minimum flows were not set. I think these are set as constant volume indoor evaporator coils. So that's why the fan power is high here. It could also be that would be again, something that you would want to make sure you can explain in the results, right? Is this a lot of indoor high static, ducted units? Then yeah, that fan power is probably going to be a little bit higher. But yeah, this VAV reheat, it seems a little bit low, right, compared to what you would expect. But again, it is running down to 30% minimum flow, and it's roughly the same airflow, right? So you're going to see some reduction. But good question. And also the DOAS and the VRF option is running constant volume. So that's another reason for it to be a little bit higher. So other things to check. So for the VAV one, one thing you might be looking at is to see how, how the VAV boxes are actually responding and seeing whether or not they're going down to their minimum. You see there's a couple outliers here in heating mode where the boxes are, the system is getting absolutely massive, and you've auto-sized here, so those are kind of unrealistic. But through the summer, it's kind of operating, around 40,000 CFM, and in the winter, you're seeing it kind of hitting down to that, say 15,000 CFM minimum box position. So for the most part, it looks, again, like it's operating correctly. Supplier temperature, you're seeing a pretty good reset between, 54 to, well, should be 55 to 65, but that's working, fairly well. But one thing to note here is, right, you're supplying, 55 degree in the wintertime, right? So there might be something to look at as to why you're getting, cooler supply temperatures in the winter than the summer. But you are seeing a lot of nice resetting in the middle of the summer, which is helping with the reheat problem. Other things to look at, how your economizer is actually operating, right? In this case, you're getting a lot of winter and shoulder season economizing, and you're going down to your minimum, fraction required in the middle of the summer. So looks like it's running fairly well. And then look at actual space temperatures. In this case, you're getting some drop-offs at the beginning and the end of the year, but for the most part, through the summer, maintaining fairly consistent temperatures, and the winter, fairly consistent temperatures. But if you were seeing a lot more variation throughout the year, you might, want to check and make sure that your fans are actually cycling on when they should be. So, and again, this is, in this case specifically, that's during a holiday period, so it's off. So the system is just floating as low as it's going to go. And, something else, we won't talk about it specifically, but there are, models that are being used now for resilience. So that might be, a question of if you were looking at envelope, for example, as an option of looking how long it takes for a building to fall out of, comfort zone. So if you turn all the HVAC system off and let the building sit, like what actually happens. So, but that low point there is based on occupied off hours. Yeah, so what happens when you actually fix that, right? So this is saying, well, what happens if you fall below your minimum setback, right? This is just letting it offset. Okay, well, let's allow the system to cycle on. If it gets down to below the 65 setback that we set in heating or above, you know, the 85 in cooling. So again, the fans are going to run a lot more, but you're going to see a much tighter space temperature control. So another thing to do that we noticed, again, if you go back to the outside air, it looks like the outside air damper was open basically 24 hours a day, and it was never actually going to a closed position. So one thing you could do there, again, good energy savings, this is a good measure we find for a lot of existing buildings, is set the damper back to 0 when you don't have any requirement for it, or nearly to 0 when you have no occupancy in the building. So you'll see once you've made that change, you see a lot of hours when you see that the outside air dampers are closed. So Jose asked, what are factors that may affect the total unmet hours? I mean, there's a lot of things. It could be that you're undersized the system. I'd say that's a fairly common, both on the air side and your capacity of coils, like whatever heating and cooling equipment's in the zone. Minimum box positions on VAVs tend to cause a lot of problems with that. Yeah, those are kind of the most common ones, but I think it very much depends on what you have. A lot of times you might have high solar gains in adjacent zones as well that weren't separated when you were doing your thermal zoning. So you might have internal heat transfer from one zone to another that's causing unmet hours as well. Unmet hours is a whole nother, we could talk 6 hours about that. So, so what happened when you actually changed those? We'll talk about these two fixes, right? So the fix of keeping your indoor zone temperature a little bit tighter so you're not floating so much, and fixing this outdoor air fraction problem. So once you allow the fans to cycle on, you see that, you know, we're increasing energy use fairly substantially, and that's fan energy is going up, but you're also heating the building quite a bit more because you're not letting it just drop out, you know, drop at night to whatever temperature it drops to. So you're doing that, but fixing that outside air, you know, and turning those off at night, basically closing the dampers at night, is bringing it back to be very similar to where you had the initial results. Yeah. So what does it look like as well in your supply airflow? Once you made the fixes as well here, you're seeing that you're getting rid of all of these crazy hours when the system is, you know, 40 degrees and it's oversizing the system pretty drastically to try to heat the building back up during that warm up period.
Yeah. Sam, you've got a couple comments.
Okay. We talked about unmet hours. Are these graphs typical for simulation? So no, these graphs, and that's a great question. These graphs are all generated from an hourly report. So in this case, we've taken supply airflow as a data point for the main, in this case, this is this large VAV rooftop unit. So we've taken an hourly data point, which is an output from the model every hour, and we've just plotted it on a line graph. So this is every single hour of data. So these are not generated automatically, but it is fairly simple just to export that 8760 data set out of the model, and a lot of them will automatically export it for you, and then you just need to dump it into Excel or another spreadsheet tool to generate these kinds of plots. So some of them will do it for you, and I think there's, you know, more and more you're seeing more graphical interface support that'll help look at some of these things. So some tools do have ways to look at the output directly in it. Some of them you might have to export this and then visualize it yourself. Other things to look at, again, this is the same hourly data point, is look at the load on cooling coils. Kind of makes sense from a cooling point of view that you're getting, you know, peak load through the summer with a nice bell-shaped curve. Same with your central heating coil and your reheat coils. So you're not getting any major reheat in the summer, which is great. But you will see the reheat coils are sized larger than your main central, which is fairly typical. Looking at EER, this is again another way just to visualize. This is the same 8760 set of data, right? So at your hottest conditions, whenever those might be, you're kind of operating right around that 10 EER. But you're getting a lot of hours when it's, you know, part load performance include and outside air conditions that are less than the design. So you're getting a much higher general operating EER. You can also look at fan demand. So again, you're seeing, that fan curve that we modeled, follows it exactly. Again, this is just a mathematical curve that we're including for the fan as it unloads based on supplier. So in this case, below, there's sort of a minimum threshold that the fan has been modeled below 15,000 CFM, so it's constant once you get there. So again, once we've made all of those changes, other ways to visualize this are to look at total site EUI. So an example here is the VRF is substantially lower. If you look at total, once you include the gas and it's an all-electric system, it's much lower. From a source point of view, the VAV and the VRF kind of operate fairly similarly. And from a cost point of view, the VAV reheat, wins out just a little bit, but the variation on energy cost is quite low, right? You're talking $2,000 or $3,000 variation. So that might not be something that is going to drive a decision from an owner, to pick that. And then from an emissions point of view, so again, other things that are becoming more common to look at, that VAV reheat has the lowest emissions. And that could just be, again, because the electric emissions factor for this specific location might be a little bit higher than gas. So, but again, just ways to visualize, the different metrics that most projects are being reported. I'd say these are the four most common, at least on an annual basis for most projects. So applying this specific to St. Louis again, so we'll talk about why that carbon emission factor, again, why this VRF is so high is that the pounds per megawatt hour for St. Louis are higher than other places. If you ran the same simulation in New York, you would have a much different breakdown on the carbon emissions. Your energy cost would actually be very different as well. So again, important thing to note, the metrics do matter. Cost of electricity and your source factors and your carbon factors, again, would very much change. Any of these metrics that you change in terms of your assumptions for utility cost or carbon emissions will obviously change, source energy emissions and cost. So be very clear with your assumptions when you're making these and be very clear to state your inputs for your model. So what happens if we move that same project to California? So on an energy cost basis, if we look back here, you'll see, we were at 67 to 64,000. On a cost basis here, you're going in that same range. In California would, almost triple the cost, close to triple the cost, just based on the rates in California, right? That you're paying closer to 30 cents a kilowatt hour and $20, 30 cents a kilowatt hour and $20 a kilowatt. Gas rates are roughly the same, right? So in that case, your all electric system in California is going to be much more expensive to operate. What does that look like on an emissions basis, right? So in this case, gas is staying the same, but your carbon emissions are getting cut by a third, right? So in California, which has a lot of solar, a lot of renewables, nuclear, we're going from 1,600 pounds per megawatt hour to 515. In this case, on a carbon emissions basis, your VRF looks great, right? It is the lowest because it's all electric. The electric grid in California is much cleaner. So again, using those factors, making sure you're using the right numbers, looking up your e-grid numbers can make a big difference. So I'm not going to run through the exercises just based on where we are on time, but something to think about, what other non-HVAC characteristics of a new building project might affect the performance of the different HVAC types. So if you have some thoughts, put them in the chat. We're at 2:15. We'll run through one more example and then we'll take actually, maybe we'll do a break now. Does that work, Drew? We'll do a quick, we'll say a 7-8 minute break right now.
Yeah, I think we need to give people a break.
Okay. Yeah, we've got a little over an hour left, so we're going to run a little bit long, but that's fine. So let's come back. It's 2:16 on the East Coast right now, so let's come back at 2:22, and we will get restarted. Thank you. And just to answer Stephen's question, first question. The emission factors, those are from EPA, he asked, and I said, those ones that are used in there are from eGrid, which yes, is EPA is the one who reports that data. All right, everybody, we are back and we're gonna keep on moving. We'll try not to go too far over today, but likely we'll probably be 15 or 20 minutes long, so hopefully everybody can stay with us. We'll keep moving. So next up in the HVAC comparison, we'll be looking at different chiller options. So in this case, we're looking at 2 different air-cooled chillers, and the question here is, what's the most efficient option, right? And efficient could be, again, different things. It could be energy cost, it could be energy, it could be carbon emissions, but something to consider, when you're framing this analysis, make sure what it looks like. The 2 chillers have different full load and part load performance. So how do we approach the modeling? First, you're going to collect the data. So go to the manufacturers, get the cut sheets, spec sheets, figure out how to, translate those cut sheets into model inputs, and then simulate them and compare the performance and do a quality review. So what goes into a chiller model? So in a chiller model, this is, again, getting a little more into the weeds of what you actually need to look at. But you'll need to have a load that goes, associated with, chilled water. So that'll be your some of your coil loads that we've been talking about before, and the outdoor conditions that get fed into the chiller model. That model outputs the energy demand at each time step. And so what goes into that model? You'll generally need the capacity, so how many tons, how many BTUs per hour, the efficiency, and then you'll need to look at what happens to those inputs, so capacity and efficiency, at different temperatures and different part load ratios, right? So a chiller is going to see lots of different operational parameters, different outdoor conditions, particularly for an air-cooled chiller, and lots of different part load performance. So these equations tend to be polynomials, and again, they represent changes in performance under the varying conditions. So one example first is that capacity varies as a function of temperature, right? So the rated condition here is 95-degree outside. This is how air-cooled chillers get tested, and 44-degree chilled water temperature, right? So that is the rated condition. But when you look at increase of chilled water temperature, your total capacity actually goes up a little bit, and as your chilled water temperature goes down, it goes down a little bit. So this is an example of 100, air-cooled chiller, again, a larger, over 150 ton. But you also need to look what happens at outdoor air temperature, right? So the rated condition is here. As air temperature goes up, capacity goes down. As air temperature goes down, your capacity of your chiller goes up. So these need to be accounted for. What does that actually look like when you plot these curves? They actually end up being surface plots, right? Where you have 3 variables that are being changed here. Well, 2 variables that are being changed that affect your total capacity. So outdoor air temperature, chilled water affect your capacity. So again, just visualizing what that actually looks like in terms of what you have to input to the model. A lot of these curves are prepackaged, and you can create these curves custom from manufacturer's data as well. But again, if you're doing a chiller example, you probably want to be creating these curves yourself. So same thing goes for efficiency, where efficiency is rated based on the chilled water supply temperature and an outdoor air temperature. So there's a rated condition that varies. The efficiency will go down a little bit based on chilled water supply temperature or up, depending. And again, EIR, just for reference, this is 1 over the COP. So when the EIR is actually going down here, that's actually an increase in COP. So lower chilled water supply is a better COP number. Same thing here, again, inverse of COP. So outdoor air conditions, it's actually getting worse. Outdoor air conditions going down, you're actually getting better performance. So again, it's a surface plot where you can kind of figure out where your operating conditions will be. But inside the model, this surface is actually captured as a polynomial equation, right? And that so at every operating condition, you can determine what the efficiency is, and then the previous one what the capacity is. And the efficiency also will vary as a function of part load ratio, right? So in this case, a straight sort of unloading curve that you get at 80%, you're getting 80% EIR, right? So you have to account for that as well and understand how it unloads. If you have a multi-compressor system, right, you might have more distinct blocks. If they have variable speed compressors, you might have a more of a linear line like this one. So what does that actually look like in terms of part load, right? You end up getting fairly consistent down, and then once you get into low loads, you kind of get this degradation in performance. So these are examples of what these curves look like mathematically, right? This is again, if you go to 90.1 2022, all of these equations, these are standard equations you can use for generally for your baseline. They're usually pretty good if you don't have data from your chiller manufacturer. But if you're doing a chiller comparison, you might want to go get actual actual data from the manufacturer. So you'll need capacity, efficiency, and then you need these three curves, right? So you might gather them, right? And this is an example from a selection of a chiller that has, variation in load, which shows your, total input power is changing and your efficiency is changing as a function of the different load. But what it doesn't do is it doesn't actually change the evaporator temperature, right? So that's a fixed evaporator temperature. So you don't have an understanding of what happens if the chilled water temperature is increasing. So let's apply that same chiller to the same project. So this is a 2-story school. And what happens when we look at these two options, right? So same capacity of the units, full load design efficiency of number 2 is a little bit higher kW per ton than number 1. But when we look at, and that's at 105 and 42, at the rated condition, right, they might look a lot closer. So you might have 1.1 to 1.0, right? But the actual design condition might be slightly different. That's also something to be considerate of when you're building your models, is whether your software is looking for the rated value or the design value. And in some cases, you can specify whether it's rated or designed. But be aware that you might get very different, especially on the capacity side and efficiency side, you can have very different numbers, whether it's, the actual design or the rated and tested. So if you look at the performance in terms of part load, you'll see that chiller 1, the blue line kind of unloads, and then the efficiency gets really terrible at part load, right? You kind of degrade when you get down low. Chiller 2 pretty much is unloading almost linearly, so likely has a variable speed compressors and stage compressors. Yeah, and you want to use actual if you're going to be creating these yourself, right? You want to be using the design data where you're actually going to be supplying and not the rated numbers. So what do you want to do here? What are the steps here? So basically you're going to take those data points that you have, you'll translate them into the BEM software that you're using. You might be doing a curve fit to take those data points that you have and turn them into those cubic and bicubic equations to determine the coefficients. Some softwares, you can just put that data in and it will calculate it for you. You might go grab some pre-existing curves that look similar. So, the ASHRAE standard has a lot of software, a lot of softwares have pre-packaged for different types of air-cooled chillers and water-cooled chillers. You can go look at the ACM manual in California. There's also good data there as well. So, or you could have some combination of pre-existing and new ones. You could compare them again as sensitivity. So, so you run the model with each chiller and you compare the results. Okay? So in this case, in terms of total electricity, chiller 2 is running, is using less electricity. In this case, you look at peak demand. Chiller number 2 has a higher peak demand. And in terms of total electric costs, chiller 2 is running slightly less, so $4,000 less. So again, just things that you might be looking at that might be important, right? And particularly you might be looking at demand because you might have a sizing constraint on your electric system. You could have large demand charges from your electric utility. So, what are you going to do now to look at, ensure that you've modeled this accurately and that you have, a good comparison between the two chiller options. So, some things to do here is look at your weather data, look at loop chilled water loop loads, look at flows and temperatures, and check efficiencies, right? So we're looking at chillers, so we're going to focus on the things that are being impacted by the chiller change. So first is weather. Make sure that that actually lines up with that you selected the correct weather file for your location. And if you have actual year, more recent weather data, that usually is a better indicator of actual performance. So this is a TMY set for St. Louis, and that's kind of a good starting point. But I would imagine if you grab a current year weather data that you're going to be substantially higher in the summer up here when you actually look at your peaks, right? So this is a more TMY tends to be a little bit more smoothed out. Next is to look at chilled water load, right? So this is tonnage. Make sure it kind of follows a similar bell curve that you would imagine. You do have some operational chiller time down here, in the sort of shoulder season and getting into the winter, you might be, looking at, potentially having an economizer or some sort of other function to allow free cooling during those times of year, right? But you might also want to see that might be a control problem, that you actually are allowing the chiller to run, down that load. You might have, pan heaters or something else that's running to keep the chiller operational during cold temperatures. Another way to visualize, again, this is an 8760 plot, is to plot outdoor air temperature versus your hourly, load, and make sure you're actually seeing the load on the chiller, load on the building itself, and then the chiller itself, dropping as you get lower temperatures. So, but this could also indicate, if you had a data point that was at a low outside air temperature with a high chilled water load, that might indicate, that there's something going on. You might need to go check it in the model. Also look at the ranges, of hours per year in the percentage, load range, how many tons are on your system. Make sure you have a good spread and then you're not, running full out at 100%, or you're running everything at like 10% load. So that's a good way to look, is just by frequency of data. In this case, this is not super indicative, but it tells you that these are both constant volume and constant temperature, right? So you're providing fixed flow rate, and you're providing fixed chilled water temperature. So easy way to check. If you see these numbers change and that's not what the controls are, that would indicate something is not being modeled correctly. And then finally, looking at efficiencies, right? So looking at your unloading curves and how they're, and we noticed that chiller one had a worse performance. Again, this is even probably further off the chart than I believe what the spec sheet said, but it should have a worse unloading curve than you have in chiller two. So again, another way just to visualize and check your data. And then you can also do that same. So this is against load against efficiency. You can also do, efficiency against outside air temperature. So again, making sure that the model is accurately following what you get from the manufacturer. So other things to look at for chilled water plant, you could be looking at air versus water cooled. In that case, you might also need to be including, water savings or potential water consumption, water side economizer, or an integrated economizer and an air cooled chiller. How you're staging chillers, if you have a larger plant, multiple sizes, you could have heat recovery chillers as well, where you're doing, simultaneous heating and cooling. And then temperature controls and how you're controlling pumps as well, right? So in this case, we weren't really looking at changing these last two, but there's a lot of variation you could see from those two options as well. Yep. And then Encyclopedia, we'll plug it once more. There's a lot more in there about just general operation and model types for chillers. So next we have post-occupancy. Drew, are we switching here, or am I going? We'll look at our schedule.
Sorry, you're welcome to keep going. You do have a couple questions though.
Okay. Do you want me to cover this one, then we'll run through? You can take the last one. Okay. Sure. Questions. Okay, so Sean was saying, if we go back a little bit, yeah. Well, let's go back to the results. Yeah. So, and this goes, I think, for the previous one as well. Yeah, that sometimes the results the variation is so small, at least in terms of the energy or say the electric cost or something like that, that you know, it is important to, you know, use this as part of an overall strategy of presenting results, right? Because, and again, the chiller might not make a big difference in terms of first cost, right? But there could be fairly large variation in first cost if we go back to the previous example of the 3 different HVAC system options, right? There's probably a factor of 2 cost when you go to the DOAS VRF versus the other 2. So in this case, yeah, it might be, you know, you might have to look at O&M, you might have to look at the operational, you know, the maintenance package and service package that you get from the different manufacturers, you know, the timeline on getting the chillers delivered, for example, might sway it in addition to, you know, the actual performance. So yeah, in some cases it might not be a clear cut, right? $4,000 a year is not a huge swing when your total is 157, right? So it's a good point. And then Steve was saying the loads are based on capacity percentage, correct? And I said yes. So those are all, these are fractional percentages. If we look here, yeah. So those are all in yeah. So yes, confirming that. All right, and then we've got one more example here of one post-occupancy reconciliation. So this is not like a true calibrated, but it's kind of looking at, you know, once the building was in operation, just doing a check essentially. And this is sort of the first step, I would say, of doing a calibrated model. And then Drew will close us out with the calibrated model. But Drew, do you want to do this one and I'll do the Pen 2 one? Maybe
that works for me.
Okay. I will give you back control.
Okay. So talking about post-occupancy reconciliation, this is where you have a design model, but then you're trying to look at how the building actually performed and where you're having more data. So this is just a way of being able to verify some of the assumptions you made, look at any operational savings you might see from how the building's operated versus how you modeled it, and then working toward a calibrated model. So first step, typically you're trying to acquire a year of data. I really recommend if you can get 2 or 3 of utility data, and associated weather is the key thing as well. So you want to run the model against the actual weather, being able to look at what's going on and then compare that to the utility data, looking at charts and statistics and see how you're doing. So standard 209, again, that we talked about earlier yesterday, post-occupancy, any energy performance comparison kind of goes through the at least an overview of how you would go about doing that. So here are a couple of charts you might do. You might be looking at different fuels, looking at energy use, actual, and you see in this case, we underpredicted the actual, and same on the gas side. And that's not unusual because there are a lot of things that you don't know as you're doing this. Using statistics, normalized mean bias error really is kind of the key, is trying to see that we're within a range, that we're not just saying that it's close enough. In this case, a common target for that is about 5%, and you'll see that in some of the guidelines related to this. So you'll see in this case we've got an error that's actually quite a bit larger than 5% for that. So 22% when you do the calculation. So there's also the coefficient of variation of the root mean square error, and a common target of that is just about 15%. In this case, if we look at that and do the calculation, the error squared, we get a CVRMSE of about 22%, again, about the same. So a little higher than we might want. So we need to do some calibration works. So let's take a look at what's going on. Electricity, the actual outdoor monthly air temperature was a little bit higher than what we had in the original model. So the electricity related to that is higher. So we're getting some there. And similarly for gas. So there is some challenge there. So we started looking at it in a little more detail, and you see electricity, we're a little low, but peak demand's not too bad, actually, that we're kind of matching that. And gas also as well. So what might be explaining that? Well, maybe we're looking at longer hours of operation or equipment that are different from what we scheduled in our original model. And so we need to be able to do that. So Sam, do you want to take it back here or?
Where are we at in terms of slide?
Operation, we're at 370.
I guess it depends. How do you want to? I can run through these.
Okay, I'm gonna give it back to you then.
Okay. Very good. Sorry, I'm gonna jump ahead. Cool. So Drew was introducing, what the sort of statistics look like, but we're gonna run through one final example here about, more specific of dealing with the calibration for an existing building. But why do you do this? You generally are doing this if you have a larger capital investment that you're looking at for, a building. You're looking at bigger changes. You want to verify that you're getting those savings on the back end. Also looking to optimize performance for future operation of the building. So it also can help, the modeler actually learn more when you go back and do a calibration, because it'll help you understand how good were your initial assumptions, were the initial savings that you potentially had. If you did a first model, for example, were the savings good? Were they in the right range? Was the building performing as you expected? And other places to improve, right? A lot of times when you build these calibrated models, you end up finding other inefficiencies that might not be 100% clear just from the building operator. So common process, if you've worked on the building before, you'll have an existing building energy model. You'll be going to the site or collecting additional information. You're going to update the model, check the calibration, and repeat. Generally lots of repeats here, depending on how far off you were. And in some cases, you might not have an existing model, right? You might be building a new model for this building, so the front end of this might be a lot heavier. But really, you're trying to, again, see how the building's actually performing. And ultimately, you want to be able to answer questions about, a future retrofit or, some sort of operational problem. So where does this data come from? We've talked about some of this, but again, this is actually getting into the weeds of more likely doing an energy audit. And a lot of times for the calibrated models, we end up doing a fair amount of data collection, that's nearly equivalent to getting sort of an ASH 1.5 audit done, I would say, maybe close to an ASHRAE level 2 in terms of data collection. But generally, we're pulling all utility data. You're going to get real weather data. You're going to try to look for as-built. For older buildings, you might have lots of different as-built depending on various different permutations of construction and modifications that were made to the building. Critical ones will be talking to the operator, obviously. The chief engineer, the building managers, to understand how they're running the building. There's a lot of data that you can get from them. BAS, trend logs, sub-meters if you have them, and you might be deploying short-term monitoring, systems. You might be logging individual systems. So this is fairly common. What we do if we're doing, chiller studies and things like that, we'll go log the chiller for a couple of weeks in the middle of the summer to get real power and flow data and temperature data. So things to check, again, all fairly consistent with what we've talked about before, but a lot of things that really do have a big impact in existing buildings are schedules. Obviously, those are big ones in terms of when stuff's turning on and off. Set point boxes, minimum set points on boxes for VAVs. Outdoor air control generally is older buildings when you're trying to calibrate them. Usually the economizers don't work so well. The dampers might be leaky. So getting a good understanding of that, and then looking at day to night, right? And sometimes we like to look at the sub-hourly data and kind of see what happens over a typical day. Those sorts of schedules will help define the inputs that go into the model. So if you have sub-meter data, for example, that's pulling light and lighting and plug loads from a specific tenant, it's a great source of data to create real schedules that mimic the exact operation of what's going on in the building. And then you might have a lot of other miscellaneous stuff that you don't know about, right? There's a big sign outside, and there's escalators and elevators and other things. So you might be, again, finding good data points to fill in the gaps where you don't have that data. So here's an example just of what you might be looking at for a calibrated model. In this case, this is a fairly quick lift on the model just to do, compare the original model, which the savings are shown here. When there was a 19% savings, and kind of from a budget to a design case. So typical kind of office building. This one had underfloor with a chiller, pretty low lighting power and daylighting controls. So the first pass on the calibration, again, this is just throwing the utility bills next to the model. You'll see that the actual electric was, nearly double on a kWh basis. Demand was fairly consistent, consistently off, not double, but it was pretty consistent value, higher in the actual building than the model. And the gas was the opposite, right? That we were predicting very, very high gas loads in the winter time, and we were seeing, less than half of that consumption. So first step, compare, right? In visual, it's really easy to see, okay, we've got, we've missed something, right? There is a miss here. So next thing is dig a little bit deeper, right? So in this case, this building specifically had, BAS system. It also had an energy monitoring system that was looking at total electric demand in the building. And we also deployed some chiller logs on this one to get chiller kW. So when we started looking at the hourly, this is in June, this is just hourly data. We were looking at, demand every 15 minutes. We looked at the actual, which is the green line versus the blue line here, and noticed that, the model was predicting basically a very low, like in the 20 kilowatt load range at night, and the building was actually closer to 500. So fairly big discrepancy, but obviously the initial model, we didn't have that data. We didn't know what it was. So once we went to the building and started asking questions, they said, oh, well, we built a data center in the building and it wasn't on the drawings. So again, things you might not know during design and things that change as you get into construction. So that was the big one, obviously, that brought, that total nighttime load. That was just this consistent background load of about 450 kilowatts that was a data center and all the cooling for that system. But there was a bunch of other little smaller things, again, to pick up in terms of garage lighting, some smaller IT, plug loads and data center for off hours, and some ventilation rates that were picked up here. So you're going to go ahead and update all those in the model, and you're going to recheck your calibration. In this case, we're making sure that our at least electric demand is there. And one way to look at this, and again, this was for an older lead M&V project, was then to update, the budget case with all of the same assumptions. So we went back to the budget case and added the data center, updated the schedules, updated the outdoor air, all the things that would need to be changed in the budget case, and then reran the baseline, or reran the proposed design, right, to understand the percentage savings. And again, this was an M&V project to understand, if they were still achieving the percentage savings that they were looking at. So even though the total costs per square foot went up in terms of operation, we were still pretty close in terms of where you were in terms of percentage savings. So again, lots of updating model, and you get answers, right? In this case, we didn't know there's a data center. So things that you will never find out. So we'll do one fairly extensive case study. This is a building in Midtown Manhattan, 1.6 million square foot, 32 floor, big extensive basement and a train station below it, that was going through preparation for a major renovation, which was, well, you'll see the extent of what was included in this one. But basically they tore it down to concrete and, reclad the entire building, gutted the HVAC for the most part. So again, there's a fairly large capital investment. So they, the intent here was to build a calibrated model that showed what the existing condition was, and then we used it over the course of almost 4 years to help make design decisions as this project morphed and changed and continued to go. So, so again, over $100 million reno on this project, even more than that now. Where do we get data for this? So there was a lot of data. And on the utility side, it was particularly interesting because every tenant had their own sub-meter and we had 15-minute data from them. So in New York, that's fairly common that you have sub-meters. So we were able to build out really detailed schedules, which I'll show you. The central plant here, which is a mix of steam and electric chillers, was also metered. So was the cooling towers. District steam, we had a 15-minute meter on. And then there was a little bit of a gas usage, but not much. And again, we have 15-minute data from the utility as well. So that's very helpful to, have a good data set to start building out this calibrated model. And then other things, we did a fairly extensive audit, lots of inspections on this building. There is a BMS, it's being upgraded now, but it was, working. And then in this case, the operating staff was the biggest source of information, right? The guy that runs this building, he's been in the building for 25 years. So he knew everything, he knew how everything ran. And that really, provided a lot of key insights into setting the controls correctly and things like that. I'm going to run back. There's a couple questions here. I realize I probably skipped a couple. Sean had asked, so thoughts on presenting issues that save energy but don't meet code or the design intent, right? Like 0 on minimums, 0 ventilation, reheats disabled. I think there's a lot. I mean, it depends, Sean, I think on, what the intent is for what you're trying to show. Those boxes were not going, the ventilation was not going to 0 at night. It was still whatever the background, minimum flow vent would be required. But I think it just depends on the client, what you're trying to achieve. Like, again, it's apples to apples comparison of system to system. So in that case, it's not like a full compliance model where you would have to be showing the ventilation at night. It's more to show like, the changes made to two similar models that have 2 different chillers in them. So it's a good question, though. And then Jose was asking another one. For an existing building constructed 30 to 50 years ago, are there resources for this kind of data? Again, CBEX has some of this data. They'll have, assemblies and things. A lot of times you'll have to go just to the building code and the energy code that was applicable for when the building was built to kind of get a better idea of those kinds of things in terms of envelope, or you're going to look at the building. I'd say a lot of times you need to go look at the building. And then can any of those properties be imported directly to software such as Open Studio? Not that I know of, like imported directly. You're still going to have to translate what you see in the field to an input into the model. So I think in any case, you're still going to have to do that. That's still going to be the engineering judgment that you'll have to make in doing those calculations. And lastly, George says, calibration mandatory to complete the model in any scenarios. I mean, calibration is never mandatory unless it's part of a, well, I'll say it's never mandatory. A lot of times there's 2 reasons that people usually are doing calibrated models. One is they have a performance contract, so there's a guaranteed savings associated with the retrofits that are being performed, and the model is being used to inform those savings numbers, and those numbers are being guaranteed by the performance contracting team. So in that case, you don't need a model, but the model is going to be much more accurate than if you didn't do it. And the other place, where we see it is where people have large renovations like this project, right, where you have significant capital being invested and you want to make sure that you are getting return on the different, components of the upgrade that you're paying for. So wouldn't say it's necessarily mandatory. And yeah, Sean, if you want to talk more about the presenting things that don't save energy and don't meet code, we could again have a fairly long conversation about that. There's a lot of buildings out there, especially existing buildings, that don't meet code, and like showing the penalty of bringing something up to meeting code generally is not that helpful, and a lot of building owners don't like to see it. But when you have to go through permits and that kind of thing, a lot of times you need to keep them informed, right? So it's a difficult line to walk. Continuing on with this, so for example, we'll look at these sub-meters. In this case, there was 44 individual tenant sub-meters. So those are the different tenants that were in the building. These data sets, again, 15-minute data sets, directly define the schedules, right? So the hourly, schedules that were used over the course of an entire year. We had 4 years of data for the building, and it specified the actual load, so the watt per square foot that was being accounted for lighting, small power, and IT. So again, this is a really good data set. It's a very accurate, right? We know that this is what the building was actually doing for the last 4 years. So it ended up creating very good schedules and very accurate schedules. On the central plant, it was the same thing. We had sub-meters for chillers, cooling towers, all the big pumps. So this helped define what the peak power was, what the average, operational sort of condition was of these different systems, and define the efficiency over all the, potential operational points, both outdoor air condition and different indoor conditions. So having this data, and again, this is for a calibrated model, really reduces the calibration time and effort, because you're not guessing on the schedules. You're not having to make minute adjustments and rerun the model and see if that fixed things, right? You kind of know that these are the schedules. This is how the building's running. It helps improve the accuracy, obviously, in this as well. So, so again, this is just kind of what the data looked like when we got it. We're just monthly, again, filling in the gaps. So you're never going to get a complete data set. We had a lot of gaps. There's vacant spaces too. For example, the one in the middle in yellow there was vacant. So you have to adjust occupancy in certain locations. And sometimes you might get the data in a format that's not super helpful, right? So this specific model was running hourly data, and we received everything in 15 minutes, right? So you have to also translate your 15-minute data into hourly data to make it useful for creating these model schedules. So, yep, go ahead. Any other questions? Okay.
No, you're good.
Okay. Okay. So what does this actually look like when you translate it into, again, these are daily profiles, month by month. What does it actually look like, right? So this is the data that actually came out of all that sub-meter data. Again, through a massive pivot table, sort of looking at, the max demand. So this is a percentage. So, we've taken we've normalized this data set out of 100, right? So 85 there is 85% of the total load. And you see the bottom end here is only at 55, right? So that's 55% total load. So one thing we noticed immediately here is that at night, this building is still running over 50% of its peak in the middle of summer, right? So we still know that, the building is still humming along and consuming a ton of energy at night. And that was one interesting point of what, kind of like pointed us in the direction of creating this calibrated model. So insights from what we found from that, what data did we gather? What did we learn that helped us calibrate it? One was that tenant energy, and again, this is just the small power, lighting, and IT was 40% of the total of the building. So there's a lot of back of house spaces here too. There's a lot of amenity, and there's a lot of chilled water that gets sent to the building next door. So that had to be removed. But it gave us, some very good data points. 2.1 megawatts of peak tenant load. The big one here that I talked about is that the nighttime load was still over a megawatt in the building, right? And so this is the graph on the right shows all of those schedules consolidated into a typical day and a typical profile, right? So we noticed that the nighttime was still really huge. And so that piqued our interest. And we started asking why. We went and talked to the chief engineer. We talked to who else was in the building, and we found a few interesting things. You'll see there's a consistent point here, a 450 kilowatt data center. We did not know about said data center. So that was running obviously 24 hours a day. That's about half of that nighttime. And then a lot of stuff was just being left on. There was no controls on lighting. A lot of large IT equipment that was running 24/7. So again, gave us very good insight into how the building was running and creating these profile schedules. But it also helped identify a couple conservation measures of things to do. One of virtualizing their data center. Not super efficient to have your own data center inside of a building like this. So they ended up, putting it into a larger data center system elsewhere and virtualizing that. And then also looking at, controls for all this sort of nighttime equipment, everything that was running at night, right? So that became part of the overall package of the future improvement. The other, well, so there's three big ones. One was the plug load nighttime stuff. The second big thing that was changed as part of this was the facade. So this is from the inside. Once we've stripped out all of the chipboard and looked at what was behind, behind the wall, basically. There was very little insulation. It kind of compacted down to the bottom below the window. They had a couple broken pieces of glass, so we were able to get those tested to get the performance of the single pane glazing that was in there with steel frames. But this gave a really good idea of what the existing condition was, right? You don't get this very often, but in this case, we see that there's, basically uninsulated cavity, single pane windows, the floor to floor, the slab basically extends all the way out into the, past the thermal plane, and it's basically a thermal bridge to the outside. So, and I'll show you what the new version looks like when we get there. On the HVAC, where did we get information? So obviously did an energy audit to get all of the information from the data. We also looked at the BMS submeter. So the main systems here were two large steam absorbers fired off the district steam system in New York and two big electrical machines. They were running the absorbers basically to cut peak demand in the summertime, so they were only really firing them June, July, August, September. And then the electric machines are kind of the base load for the rest of the year. And they had four big core constant air volume systems, two serving the upper, two serving the lower, and then 8 perimeter ones, also half going up, half going down. Very high static pressure, 13-inch static pressure perimeter induction units. So what was the model? So we went through all this, we calibrated it. I'm not going to run through everything, but what did we actually use it for, and what were the, what was the basis that came out of it, and what was it useful for? So first was the facade, which this is a picture of the new facade now. I don't know if I do on the next slide, I'll show you, of, actually what they ended up with. And they went from a double pane specification to a triple pane specification because of the model. The model proved out that it would pay for itself in less than 4 years. So that to add an extra pane structure was okay, so they were able to add that. It helped with choice of HVAC system. So, they were looking to replace in kind, but we ended up with, ventilation being separated and adding DOAS units and a full fan coil, replacement of all the perimeter induction units. So that was something else that came out of the model. We were able to test all these different options. We also did a fairly extensive tenant efficiency package, and this was helping for leasing, to create like a good, better, best sort of leasing strategy for them in terms of the package of fit out that they would offer to future tenants. We also looked at electrification, hardening on the electric system, and then lots of value engineering, which is still going on a little bit today. So overall, we ran over 80 ECMs for energy conservation measures for this model over the course of about 3.5, 4 years, both base building and tenant related. So the facade, just to show before and after, the left is before, after on the right. So again, they added a whole another basically bay of glass. They took out these high pressure risers, much cleaner look. They lowered the sill a little bit for a much higher, window glazed area, better view, better daylighting. So the analysis here was carbon. Again, a lot of stuff driven in New York is about local law 97. That's carbon emissions related. But it was also being looked at reducing mechanical equipment size. So we knew we were adding more glass. So it's going to become a glassier building. How do we still, maintain the existing equipment size or make it smaller? So in this case, the ultimate result was a triple pane, low E system. They had started with double, but the model proved out again that there was such substantial reduction in, heat gains, heat losses, so total loads, as well as operational energy from this, that they were able to justify the move to triple. So even by increasing the area by 43%, we still see massive reductions in heat loss and heat gain, just because of the performance of the framing system and the glass itself. So also interesting, they kind of did this from the outside in terms of building it. They kind of, would tear out the inside and then reclad over the outside. So all of that, all of the demo and everything happened towards the inside of the building. So there wasn't scaffolding, that was just these small little bays that they were moving along. So it was pretty cool. On the HVAC side, There was, again, a lot of options here. There was a lot of different fan coil types. They were looking at chiller replacements. Again, this is just kind of presenting all of the different scenarios that were looked at. But the big one was to look at what happens with these chillers. Are we going to keep the steam chillers or not? They ended up keeping one steam chiller, partially because they couldn't get it out of the building because it's so huge and it was built in place. But they did upgrade both of the existing old centrifugal machines with new, variable speed units. They did a full reno on the cooling tower. So again, we modeled the cooling tower. And the way we presented the data here is that we had a design, say back in September of 2019, that was what was on the drawings, and that was our first step. We had the calibrated baseline, and we made all those changes. And you'll see there was very little electric change. It actually went up a little bit once we looked at the existing design, and steam went down a little bit. But a lot of these things didn't have a whole lot of change, and this was kind of before we were looking at this triple pane glass option, right? So these were all, kind of isolated and modeled out separately. And there wasn't a very big change, but the big change was the DOAS, right? When we got away, we got those high pressure static systems out, we got the fan coils in place. That made a huge difference in the overall. So there were, again, a ton of different units run on this fan coil system, and we were able to model all the different, static pressures of all these different systems and compare them. At the end of the day, the variation was very slight, and it ended up being the size of the unit ended up driving which one was installed. So on the tenant side, it's interesting just to say, going back to standard 209, we had a big charrette with the whole design team and all leasing and a bunch of people to figure out, what are things that tenants are looking for. And this is in 2019, so we were looking forward to 2025 when the building will be open. Of what sort of guidelines we should have for future tenants. So looking out to future energy codes, in development to kind of come up with these packages of ECM. So a little bit interesting use of a calibrated model, because generally you're looking more at base building, big stuff. But in this case, we were kind of looking at lots of tenant things, which is cool because it's a kind of a nice use. You already have this model built. These are great things that you can run through it. So there's packages that were sort of defined as standard today, fairly low cost. Package 2 is a little bit higher cost, maybe a little bit more outside of the box in terms of somebody designing to meet these requirements. And then the third package was, really aggressive on lighting and kind of having these zoned areas within the floor plates that would be, over time, if people are there, they kind of work there, have really, really tight controls on all the plug loads and things like that. So that's kind of the way we ended up grouping it, working with the architect and the leasing team. And again, just a way of presenting the data, again, in this case, we were looking at actually 2013, because that was the energy code in New York City when this project was started, and looking at a, basic compliance system, and then looking at the different packages. And in this case, looking at a comparison against a carbon limit. And so this is in New York City. There's a carbon emission limit that changes 2024 and then 2030 and then 2035. So they were looking at the 2030 limit in this case to make sure that they would be below that limit. And then we also overlaid this on top of, some of these tenant packages with, the other sort of changes that are being made, right? So we didn't do a full-blown parametric analysis of all the different options, but we did end up overlaying, the tenant package on top of the glass with the fan coils to kind of say, okay, this is where you're going to final get, right? And again, just another way of looking at it. They were looking at doing an initial replacement of just putting in a new induction unit, which again is not going to change a lot for their energy consumption. It's basically, a little more efficient, a little less static, but at the end of the day, didn't cause a big impact. So again, visually and through the numbers, we're able to convince them, right, that it's a better solution. You can get, over 30% improvement. This is even with adding additional 40% glass to the building, right? So again, just ways of visualizing the data to help clients see it. And then there was also a request to look at electrification. So this is kind of what happens if you dump the district steam. The proposed plan was to keep all that in place. And we kind of went through this analysis to see what would it take to get off of the steam system. And in this case, there's kind of, like for like electric chillers for the steam units, but add some electric boilers, which is a big, obviously, electric demand. heat recovery chillers, or then look at some sort of hybrid with some heat pump chillers. So we did get a cost consultant involved at this point to kind of look at the variation in price on, alts 1, 2, and 3, just to kind of see the difference. We ran, scenarios in terms of carbon emissions just to see, and obviously that number 1 with the electric boiler was not a good choice. And the other 2 showed an increase just because electric still has a slightly higher emission rate compared to the district steam system. Stepping back, so that's kind of the end of that one. But there's, kind of thinking about calibration as a whole, right? You can really jump into the weeds and get, way into the details like we did on that one. But there is kind of a lesser level of effort that's kind of more like a utility benchmark and kind of a rough model to get breakdown. It's more like an H2 type, analysis. But you're getting big picture. You're kind of helping them decide where they should be focusing their effort on the next step, right? So this might be like, well, we've got, we want to plan for a modernization, but we don't know which systems to go after. So you're kind of looking at end of life of systems. You might be figuring out, do you need to upgrade glass or plant? Generally lower fee, lower effort, for something like that. And you get to the detailed, calibration, and this, again, like what we just talked about for that last high-rise building, right? Is that in this case, they knew they had a budget. They knew they wanted to reposition the building. And it was a multi-year, project in that case to get the level of accuracy that they wanted in order to make financial decisions moving forward with the project. So again, it can be very different level. You could be talking about, a couple months or a month or less for something sort of at this sort of 30,000 foot level, or, you could be spending 5 to 6 months to build a calibrated model and then, model out options for many years. So, all right, we are already at 3:15. We've got about 15 minutes left, so I hope everybody can stay with us. I appreciate it. We'll try to run out. So the last section here is just about, once you have this model, or you've been, you won the RFP and you have a project, how do you actually effectively, make an impact of what you're doing, right? And obviously, you're hoping that since someone signed up, your team do the energy model, right? That they have, that they want to be able to use your services to help make an impact, right? But a lot of times you have to help the client and do that. So we'll talk a little bit about planning, analysis, and communication for, when you're running a model and you're presenting a model and results and things like that. So we've touched on some of this, but it's good to reiterate it, because at the end of the day, if you don't meet the client requirements and they're not satisfied, they're not going to come back and ask you on the next project, right? So the important thing is to make sure you're relevant, so you're answering their questions, you're accurate, you're timely, and you present the data in a way that can be understood by the people asking for it, right? So those are sort of the 4 key items. And if you don't take anything else away from that, in terms of presenting data, keep those 4 things in mind. So what does it look like from a planning point of view? And we've talked about this, we kind of talked about it all day yesterday and today as well, is like, first off, understanding what you're trying to answer with the analysis, right? So framing the goal of what you're trying to answer, what question is there that needs to be solved. And then, again, within your team, and every team structure is a little bit different, but, doing resourcing, when does the client need it by, working backwards to that, who's doing the work, how many people, who's doing the review, how are you gathering the information, right? So set that up with the client ahead of time to understand who is going to be doing the data collection, how you're going to be getting what you need. In terms of having good analysis, and we say accurate analysis that is appropriate for the question that you're trying to answer, right? So make sure you're using the right tool. Make sure you have a tool that will model the things that you're trying to simulate. So we talked about that before. If you're going to be looking at radiant systems, make sure you have a tool that can model radiant systems accurately. And if there's questions that came out of the design, so for example, they're looking at HVAC, make sure you're running the right systems, right? Make sure you ask the questions, you verify your inputs with the design team. Use the right amount of detail. So don't spend a lot of time on something that is not going to have a huge impact on the model, really. And that'll help you speed up your process and make sure that you turn things around in a good amount of time. Use good sources where you don't have data. So again, look at all the data sources that we provided in this course, document them, and have somebody review it, right? Have something in place where you can do a review process. Coordination with the client, and these are all probably preaching to the choir a little bit, but setting out goals and targets and a schedule up front usually saves a lot of headache and time later instead of just kind of jumping into things. So we tend to try to have at least a 15-minute like up front with the client and say, like, here's the expectation, here's what you're going to get, here's who's going to be the point of contact, and if you have any issues, this is how we're going to resolve them, right? And so that's kind of key to have up front, and also to make sure that they know that they're going to be getting information from you that they need to verify, right? If you don't tell them up front that you're going to ask for verification on inputs, they probably won't respond to them. They've got other things to do. They've got drawings, different people to coordinate with. So, and then finally on the presentation side, make sure that you're answering the design questions in the presentation, that it's clear. Focus only on the key pieces. You don't need to show. Generally, clients are not going to be asking for every single piece of data that comes out of the model. They're going to want to know what's the most cost-effective option. What's it going to cost to build? How much am I going to save, right? And make sure it's easy to read and easy to format, right? Because a lot of times you might have different age groups of people that will be receiving the information. So you got to make sure that visually it's acceptable by everybody that can see it as well. And technically, I guess the other thing is, if it is a group of engineers, it can probably be a little bit more technical, right, than if you're going to a building owner or developer who's not going to get into the weeds as much on the technical side. Some other best practices, and these are things to take home with you, print out, think about them. When you're doing this, and whether it's a calibrated model or a design model or compliance model, make small changes and run the model, right? And check the results, make sure they make sense, and then make another change. If you make 50 or 100 changes at one time and rerun the model and something doesn't make sense, you might not know exactly which change it was that caused the unknown. Document everything, right? Document your calcs, inputs, assumptions. Have a standard format for that. If you don't have one, I would suggest developing one fairly quickly. It will help save a lot of time, and it'll save a lot of headache in the future. Save everything frequently. These tools love to crash. If you've done any amount of models, I'm sure you've lost some before. So make sure you save them, you back them up consistently. Have some sort of process for sharing documents. Again, these things can get big. You can have large files, you can have lots of versions of files that can easily eat up your storage space. Also make sure that people aren't duplicating files and overwriting things, right? So just make sure there's a good format for how you're saving things. And then in terms of doing reviews, and this is something we hold really tightly in-house that we do at Code Green, is we review multiple times on a single model, right? So you're not just getting a completed model at the end of the day and doing a full review of every system. You're kind of checking in periodically to make sure that the model's going in the right direction. Make sure you're checking zoning, you're checking envelope, gains, HVAC along the way, so that when you get to the final model and you have a total and you're comparing energy to energy between the proposed and a baseline, right? You don't have to go back and re-review all these individual components. You've already reviewed them, you've checked them off. And that also is helpful for whoever's actually completing the model. If that, it's good insight for you if you're doing that, okay, I don't have to come back and fix the envelope anymore. We already did that. So some other best practices, again, won't go through all this, but present data that's appropriate, right? If it's technical, make sure it's easily understandable. A lot of times, I even heard it today on a call this morning that, one of my colleagues said something that, everybody should know this or something like that, right? And it's like in the room that we were in, that was not clearly the case. So you might, consider your audience and who you're presenting to, right? Some people, things that you might take for granted might not be clear for other folks that don't do this day in and day out. Again, set expectations for delivery and timing and schedules, very important. And again, this is kind of getting a little more outside of just modeling in general, but when you're doing information requests, and this is, being on both sides of this, don't send multiple requests for things. A lot of times you'll get a good response on the first 2 or 3 times you ask for something, and then after that, people will get frustrated. So if you try to package them together, it's usually easy to have good response with people. Yeah. So, and the other thing, the very last one here is just, present what you've done, with confidence. Like whatever you're putting out in front of people, make sure you've reviewed it, you're confident presenting it, and the feedback you get from the questions that are being asked by whoever's in the room, or the design team, whoever it is usually going to be very helpful and insightful to you. If there's a different direction or something else that they're thinking about, right? It'll help you understand and frame the next round of analysis. So, all right. And with that, we are done. We're only 23 minutes over. Okay. Well, thanks for everyone for staying on. Very much appreciated. And if there's any other questions, our emails are here. I know there were some things that we did not get down into the weeds on. I'd be happy to follow up, email, phone call, whatever, to let me know. Always open for feedback as well. So if you have any feedback on the course or anything that we could do better and improve. It is a little tough for the virtual format, but I think it's helpful. I appreciate everybody asking questions and posting and responding there, even though we're not face to face. So much appreciated. The end of the presentation is all the resources. So everything that we've talked about, all the standards, links for a lot of stuff that we've discussed today. All right. Well, very good. Thanks, everyone. Have a great rest of the week.